Canada is home to some of the largest megaprojects in the world. There's a $28 billion transit revolution happening in Toronto, while a $13 billion nuclear generating station is breaking records. Today, we're going to dive deep into Canada's biggest megaprojects, revealing the staggering effort the nation puts into the construction industry. Let's travel over to the Ontario Line subway, a rapid transit line under construction in Toronto. Being one of the largest and most ambitious megaprojects in Canada, this $28 billion rapid transit line will ease congestion, connect key areas, and revolutionize transportation in the largest city of Canada. The Ontario Line will be a 15.6 kilometre long subway system stretching from Exhibition Place in the west to the Ontario Science Centre in the east. It will feature 15 stations strategically designed to improve transit accessibility and reduce travel times for millions of commuters. The line is expected to serve 388,000 daily boardings, with trains arriving as frequently as every 90 seconds during peak hours. A full end-to-end journey will take just 30 minutes, compared to the 70 minutes it currently takes using existing transit options. The idea for a downtown relief line in Toronto dates back over a century, but it wasn't until the 1980s that serious planning began for a subway that would relieve pressure on the Bloor-Yonge interchange. Over the years, several proposals surfaced, including the Relief Line South project, which was meant to run from Pape Station to Osgood Station. However, in 2019, Premier Doug Ford introduced a new plan, the Ontario Line. This new plan promised faster construction, better cost efficiency, and greater network integration. Its construction began in 2022, and the Ontario Line became the flagship project of transit expansion in Toronto. The Ontario Line will be an automated, driverless subway running a mix of underground, elevated, and surface-level tracks. The line will use lighter metro vehicles, allowing for steeper grades and smaller tunnels, reducing overall construction costs. Construction officially began in 2022, with the Ontario Line expected to be fully operational by 2031. Tunnel boring machines will carve out the underground portions, while elevated tracks will be built in less dense areas. Cut and cover methods will be used in dense urban areas where deep tunneling is not feasible, such as along Queen Street and Osgood Station. Elevated tracks will be built in less congested areas, particularly north of the Don River and along the Metrolinx owned rail corridor. To ensure structural integrity and safety, engineers are using reinforced concrete tunnel linings, vibration dampening technology, and automated train control systems to enhance efficiency. The Ontario Line is expected to create over 15,000 jobs during construction and thousands of permanent transit-related positions once operational. It will reduce traffic congestion, eliminating 28,000 daily car trips and cutting down on emissions and fuel consumption. The Ontario Line is also expected to save 7.2 million litres of fuel per year, supporting local green energy initiatives and reducing carbon emissions. Let's discuss the Bruce Power Nuclear Generating Station refurbishment, one of the most significant energy infrastructure projects in Canada. With a $13 billion price tag, this initiative aims to extend the lifespan of Bruce Power, already recognized as the largest operating nuclear plant in the world. Situated on the eastern shore of Lake Huron in Ontario, the Bruce Nuclear Generating Station spans 932 hectares, making it one of the largest nuclear power facilities in the world. The plant has 8 pressurized heavy water reactors, supplying about 30% of electricity in Ontario. Since its inception in 1970, Bruce Power has been a pillar of energy security in Ontario, providing clean, reliable power to millions of people. The refurbishment project is crucial for extending the life of 6 of the 8 reactors, ensuring they continue producing carbon-free energy for at least another 40 years. Without these upgrades, Ontario would face energy supply challenges, leading to increased reliance on fossil fuels. Originally constructed between 1970 and 1987 by Ontario Hydro, the facility was known as Bruce Nuclear Power Development. However, in 1999, Ontario Hydro was restructured, and Ontario Power Generation took over operations. In 2000, Bruce Power, a private consortium, signed an 18-year lease agreement with OPG to operate the plant. This was later extended by 25 years, securing operations until 2044. Over the years, Bruce Power has seen multiple upgrades and licensing renewals from the Canadian Nuclear Safety Commission. In 2023, the station produced over 45 billion kilowatt hours of electricity, supplying 7% of total electricity consumption in Canada. With the current refurbishment, Bruce Power will maintain its status as a global leader in clean energy production. The refurbishment process is extensive and includes the replacement of major reactor components, such as steam generators, fuel channels, and pressure tubes. Since these components degrade over time due to high radiation and temperature exposure, they must be replaced to ensure long-term safety and efficiency. The first phase of reactor refurbishment began in 2020, with completion expected by 2033. To minimize risks, robotic systems are being used for precise component removal and installation. These advanced robots reduce radiation exposure for workers while improving efficiency. 3D scanning technology also assists in verifying installations and detecting structural anomalies. Additionally, Bruce Power is implementing artificial intelligence systems to monitor reactor performance in real time, ensuring smooth operations once the refurbishments are complete. This refurbishment will create 22,000 direct and indirect jobs, providing opportunities in engineering, construction, and skilled trades. The clean energy production from Bruce Power will reduce greenhouse gas emissions equivalent to removing 5 million cars from the road annually. But next up, we have to talk about the iconic Toronto Pearson Airport Mega Terminal Expansion, a $4.7 billion project that will increase airport capacity and modernize infrastructure. This ambitious expansion plan aims to address growing passenger demand, enhance operational efficiency, and introduce cutting-edge technology for a seamless travel experience. Toronto Pearson International Airport is the busiest airport in Canada, serving as a crucial hub for international and domestic flights. Over 60% of air traffic in Canada flows through Pearson, with 46 to 47 million passengers annually. By the early 2030s, this number is expected to surge to 65 million passengers per year, making expansion a critical necessity. The mega terminal expansion is part of Pearson Lift, a 10-year, multi-billion-dollar infrastructure plan. This airport transformation includes several key upgrades: a new state-of-the-art mega terminal for streamlined operations, expanded international arrivals areas to handle increased passenger traffic, and advanced baggage handling systems for seamless luggage processing. A modern modular interim terminal will add capacity for up to 7 million additional passengers. Finally, digitization and biometric upgrades will enhance the efficiency of airport security. The expansion is divided into several key phases, focusing on modernizing airport infrastructure and integrating smart technology to enhance efficiency. The infrastructure acceleration phase focuses on immediate upgrades like electrical, plumbing, and washroom renovations. With 140,000 people traveling through Pearson daily, maintaining clean and functional facilities is a top priority. The electrical system, particularly underground runway lighting cables, is also being modernized. The permanent terminal expansion phase is under planning. Officials are still evaluating whether to construct a brand new terminal or expand the existing one. This phase will include numerous airline slots for smoother flight scheduling, a high-tech baggage system, and additional lounge areas for a world-class passenger experience. Digital revitalization and climate resilience phase focuses on implementing biometric technology for faster, contactless security screening. Improvements to public transit connections are being discussed, including extending the Eglinton Crosstown West LRT directly to the airport. Furthermore, short-term baggage storage facilities will be expanded to enhance luggage management. With climate change becoming a major concern, flood-resistant infrastructure is also a key priority, following recent severe weather events that caused flooding in airport facilities. Pearson is investing in AI-driven air traffic management systems to enhance flight scheduling, reduce delays, and optimize airspace usage. The project also integrates sustainable aviation fuels, like hydrogen, requiring on-site hydrogen production facilities. New high-speed rail connections are also being considered to improve connectivity between Toronto, the GTA, and Pearson Airport. By 2035, Pearson will offer a faster and world-class travel experience, rivaling the best airports in the world. But just wait until you hear about the Newfoundland Wind Energy Project, a groundbreaking initiative harnessing the power of wind to fuel green energy transition in Canada. With a $12 billion investment, this project aims to construct one of the largest wind farms in the world. The project was first conceptualized in response to the Canadian Hydrogen Strategy in 2020, which outlined a roadmap for producing and exporting hydrogen as a major energy source. Located in Newfoundland and Labrador, the project will see the installation of over 300 wind turbines, generating more than 4 gigawatts of clean energy. This electricity will be converted into green hydrogen, a zero-emission fuel source. The project is expected to play a pivotal role in the Canadian hydrogen export market, meeting the growing demand for renewable energy solutions across the globe. The Newfoundland Wind Energy Project employs some of the most advanced wind power technologies in the world. It will be developed using a mix of onshore and offshore wind farms, maximizing efficiency and output. Unlike traditional offshore turbines that are fixed to the seabed, floating wind turbines are anchored with mooring lines. This technique allows them to be installed in deeper waters, where wind speeds are higher and more consistent. The project will use high-voltage direct current transmission lines to efficiently transfer power to hydrogen production facilities. This reduces energy loss over long distances, making it ideal for exporting power to industrial hubs. Once wind-generated electricity reaches land, it will be used to split water molecules into hydrogen and oxygen via electrolysis. This hydrogen will then be compressed and stored for export or local consumption. The Newfoundland Wind Energy Project began preliminary assessments in 2022, with full-scale construction expected to begin in mid-2025. The project will be completed in phases, with the first turbines expected to be operational by 2027. Full completion and export operations are set for 2030. This mega project is expected to bring significant economic and environmental benefits. Construction will generate over 3,000 jobs, with permanent positions in operations and maintenance. The project will make Canada a top global exporter of green hydrogen, strengthening trade partnerships with Europe and Asia. The wind farm will replace fossil fuel-based energy, cutting millions of tons of CO2 annually. It aligns with the goals of Canada in achieving net zero emissions by 2050. Next up, we have to talk about Highway 413, a massive $6 billion mega project designed to alleviate congestion and improve connectivity across the Greater Toronto Area in Ontario. This long-awaited expressway will serve as a crucial trade and commuter route, reducing travel times and fostering economic growth. Highway 413 has been in discussion for years, dating back to the early 2000s. With increasing congestion on Highway 401, one of the busiest highways in North America, traffic has worsened dramatically. This 59-kilometer expressway will link Highway 400 near Vaughan to the Highway 400 one 407th interchange near Mississauga, Milton, and Halton Hills, improving access for commuters and businesses alike. Highway 413 will include 11 major interchanges at municipal roads, enabling seamless connectivity across York, Peel, and Halton regions. The design also incorporates modern infrastructure such as carpool lots, truck inspection stations, service centres, and dedicated electric vehicle charging stations. The construction of Highway 413 will employ some of the most advanced road building technologies available. The project will employ autonomous grading equipment and GPS-controlled earth-moving machinery for underground sections, particularly where the highway intersects environmentally sensitive areas. Tunnel boring machines will be used for underground sections, while autonomous grading equipment will ensure precise leveling of the roadbed. The use of drone mapping and LiDAR scanning technology will enhance precision during construction, ensuring efficient land grading and alignment. AI-powered traffic management systems will be installed to optimize speed limits, reduce bottlenecks, and ensure real-time updates for drivers. To minimize disruption to local communities, noise barriers and dust control measures will be implemented throughout the construction phase. Unlike conventional highway projects, Highway 413 is being developed with an emphasis on environmental sustainability. Porous asphalt and noise-reducing barriers will be used to improve drainage and lower sound pollution in residential areas. The expressway will include wildlife corridors and noise barriers to reduce ecological disruption and noise pollution. Smart road technologies, including LED lighting and weather-responsive traffic signals, will further enhance efficiency while reducing the carbon footprint. Construction of Highway 413 is expected to begin in 2025, with the anticipated completion date set for the early 2030s. The expressway is expected to cut travel times by up to 30 minutes per trip, offering relief to daily commuters and businesses transporting goods. But we have to talk about the GEO expansion, a massive $21 billion transit project set to revolutionize the commuter rail network in Ontario. The GEO Transit network has been a cornerstone of the public transportation system in Ontario. It was first introduced in 1967, connecting major cities across the Greater Toronto and Hamilton area. By 2015, GO Transit was operating at near full capacity during peak hours, leading to the launch of the GEO expansion project to modernize and upgrade the existing network. The project officially broke ground in 2019, and construction is expected to be completed by 2032, bringing a fully electrified, all-day, two-way service to millions of commuters. The GEO expansion project involves a full electrification of key GEO Transit rail corridors, which will replace diesel-powered trains with cleaner, faster electric trains. This will allow for trains to run every 15 minutes or less, rather than the current hourly service in many areas. The project also includes the construction of more than 200 kilometers of new rail track, additional bridges, tunnels, and modernized rail infrastructure. Some of the key corridors undergoing upgrades include the Lakeshore West, Lakeshore East, Barrie, Kitchener, and Stouffville lines. To accommodate increased train frequency, major signal upgrades and track doubling are underway. The project also includes station enhancements with new platforms, accessibility improvements, and better connectivity between different transit systems. Union Station, the busiest transit hub in Canada, is undergoing a massive overhaul to handle higher passenger volumes and improve service efficiency. Additionally, new maintenance and storage facilities are being constructed to support the expanded fleet of electric trains. Unlike traditional diesel trains, electric trains offer a faster acceleration rate and a quieter, smoother ride. The use of overhead catenary lines for power supply ensures minimal energy loss, making the system highly efficient. Construction methods include cut and cover tunneling for underground track expansion and the use of precast concrete segments to speed up bridge and station construction. The GO expansion project will create over 8,000 jobs during construction and thousands of permanent jobs in operations and maintenance. By shifting more commuters from cars to public transit, it is projected to reduce greenhouse gas emissions by 50% across the GO network. The electrification of trains will eliminate millions of litres of diesel consumption annually, making Ontario a leader in sustainable urban transit. Let's travel over to Montreal, where an ambitious $870 million revitalization of the Olympic Park is underway. This project aims to restore one of the most iconic landmarks in Canada, Olympic Stadium, while modernizing surrounding facilities to enhance tourism, sports, and economic activity. The Montreal Olympic Stadium, originally built for the 1976 Summer Olympics, is one of the most recognizable structures in Canada. Known as the Big O, due to its unique circular shape, the stadium was designed by French architect Roger Talibert and was meant to be a futuristic sports complex. However, the venue quickly became infamous for its construction delays, massive cost overruns, and structural issues, earning it the less flattering nickname, the Big O. Despite its rocky history, the Olympic Stadium remains the largest covered stadium in Canada, with a seating capacity of over 56,000. The retractable roof of the stadium, intended to be an architectural marvel, faced constant malfunctions and was eventually replaced with a fixed, non-retractable membrane in 1998. The new roof, however, remains problematic and cannot withstand heavy snowfall, leading to partial closures and event cancellations. Now, after decades of debate, officials have committed to a long overdue restoration, ensuring the stadium remains a functional and modern venue for generations to come. This ambitious revitalization project, which began in 2022, focuses on three main objectives. The current roof, which has deteriorated over time, will be replaced with a new, more durable and weather-resistant structure. The new roof will be lightweight, energy efficient, and capable of handling harsh winters of Quebec without requiring constant repairs. The Esplanade area will be transformed into a modern public gathering space, complete with green spaces, pedestrian pathways, and new entertainment venues. Additionally, sports facilities such as the Aquatic Centre and gymnasiums will be upgraded to meet international standards. The revitalization will aim to attract more international sporting events, concerts, and large-scale exhibitions, positioning Montreal as a premier destination for global events. The project involves several complex engineering solutions, particularly for the replacement of the roof in the stadium. The new roof will be made of an ultra-lightweight tensile membrane supported by high-strength steel cables that allow for flexibility while maintaining durability. Other mechanisms include advanced seismic retrofitting to improve the structural resilience of the stadium, smart lighting systems, and energy-efficient insulation to enhance sustainability. The revitalization project is expected to be completed by 2028, with phased construction ensuring that parts of the Olympic Park remain open to the public throughout the renovation. Let's move over to the Bay du Nord oil project, a groundbreaking deep-water oil drilling initiative that is set to redefine the offshore energy industry in Canada. With a staggering $12 billion investment, this project aims to extract up to 200,000 barrels of oil per day from one of the most remote offshore basins in the world. The Bay du Nord oil project was first discovered in 2013 when oil giant Equinor, in partnership with Cenovus Energy, identified vast reserves in the Flemish Pass Basin, about 500 kilometers off the coast of Newfoundland and Labrador. Over the years, extensive geological studies confirmed that the area holds at least 500 million barrels of recoverable crude oil, making it one of the most significant offshore discoveries in Canadian history. In 2018, the Canadian government approved the project, seeing it as a key driver for economic growth. However, delays due to environmental concerns and fluctuating oil prices pushed the final investment decision to 2022. Full-scale construction is expected to begin in 2025, with the first oil expected by 2028. The Bay du Nord project employs some of the most advanced deepwater drilling and production technologies in the industry. Unlike traditional offshore platforms, this project will use a floating production, storage, and offloading vessel, allowing for efficient extraction in waters as deep as 1,200 meters. The FPSO will process crude oil on-site, separate water and gas, and store the oil before transferring it to tankers for export. This system reduces infrastructure costs and minimizes the environmental impact compared to fixed platforms. A key feature of this project is its commitment to next-generation energy efficiency and automation. The FPSO will be equipped with AI-driven monitoring systems that allow for remote operation, optimizing production and reducing human intervention in high-risk areas. The facility will also integrate carbon capture and storage technologies, ensuring compliance with Canadian emissions reduction targets. Additionally, the project will incorporate low-emission power generation systems to cut down on greenhouse gas emissions. Construction of the Bay du Nord oil project will involve some of the largest offshore engineering firms specializing in subsea infrastructure, FPSO construction, and high-pressure drilling systems. Due to the challenging deep-sea conditions, remotely operated vehicles and autonomous drilling systems will play a crucial role in building the necessary underwater pipelines and wells. The project will also require a significant fleet of supply vessels and helicopters to transport equipment and personnel. The economic and employment benefits of the Bay du Nord project will be immense. It is expected to create over 10,000 direct and indirect jobs during construction and sustain thousands of high-paying jobs throughout its operational life. The project will also generate billions in royalties and taxes for the Newfoundland and Labrador government, supporting local infrastructure and social programs. Let's discuss the QEW Skyway Bridge replacement, a $100 million infrastructure upgrade that will enhance transportation across Ontario. This ambitious project aims to replace the aging Burlington Bay James N. Allen Skyway, a vital corridor on the Queen Elizabeth Way Highway, ensuring safer and more efficient travel for thousands of commuters and freight vehicles daily. The Burlington Bay Skyway has been a crucial link between Hamilton and Burlington, Ontario, since it was first opened in 1958. The original bridge was constructed to accommodate growing traffic between Toronto and Niagara. But as traffic volume surged over the decades, an additional parallel bridge was built in 1985 to handle the increasing demand. However, after years of wear and tear, the bridge is in urgent need of replacement to meet modern safety and engineering standards. The QEW Skyway Bridge Replacement Project will feature a reinforced steel and concrete structure designed to enhance load capacity, improve durability, and increase resilience against extreme weather conditions. One of its primary upgrades is the widening of lanes to ease congestion and allow for better traffic flow. The new bridge will also incorporate state-of-the-art seismic protection measures, ensuring it can withstand potential earthquakes and other structural stresses. To minimize traffic disruption, the construction process will follow a phased approach, allowing sections of the existing bridge to remain operational while new components are built. The project will use precast concrete segments, a technique that allows for faster and more efficient assembly while reducing construction time. Hydraulic jacks and launching gantries will be utilized to carefully place bridge segments without the need for full road closures, ensuring minimal inconvenience to travelers. One of the most notable innovations in this project is the use of advanced corrosion-resistant materials. High-performance epoxy-coated rebar and stainless steel reinforcements will be used to extend the lifespan of the bridge and reduce future maintenance costs. The construction team will also implement drilled shaft foundations for added stability, ensuring the bridge can support heavier vehicle loads while minimizing long-term structural degradation. Construction on the QEW Skyway bridge replacement is expected to begin in 2025 and be completed by 2029. Throughout the construction period, traffic management strategies such as temporary lane shifts, smart traffic monitoring systems, and noise reduction barriers will be implemented to minimize disruption to local residents and commuters. This mega project is expected to bring long-term economic and environmental benefits. The improved bridge will enhance trade and transportation efficiency, supporting Ontario's growing economy. The new structure will also reduce traffic bottlenecks, lowering fuel consumption and cutting vehicle emissions.
Welcome to the Muskrat Falls Project, a colossal hydroelectric power station on the lower Churchill River in Labrador. Did you know that the Muskrat Falls project spans over 100 square kilometers? The project harnesses the power of water, generating up to 824 megawatts of electricity, enough to light up over 500,000 homes. Construction kicked off in 2013 and, amidst various challenges, wrapped up in late 2020. The scale of this endeavor is staggering, with a final cost soaring to approximately 12.7 billion Canadian dollars. Originally estimated at 7.4 billion, the financial scope ballooned due to unforeseen geological challenges and logistical complexities. The construction of the dam itself is a feat to behold. The main dam, made from over 2.2 million cubic meters of concrete, stretches across 32 meters in height and an impressive 432 meters in length. The project utilized innovative construction techniques, such as the extensive use of large-scale prefabricated modules to speed up the construction process and reduce the environmental impact. The harsh weather conditions of Labrador, with freezing temperatures and heavy snow, tested the mettle of every worker on site. Muskrat Falls also integrates cutting-edge technology with a series of 204-kilometer transmission lines, known as the Labrador Island Link, which connect the power generated from the falls to the population centers. This technological marvel includes software that allows the power flow to be adjusted in real time, optimizing energy distribution based on current demand and supply conditions. Muskrat Falls is connected to the island of Newfoundland by a subsea cable spanning nearly 30 kilometers across the seabed of the Strait of Belle Isle. This is one of the longest subsea electricity cables in the world, a little shorter than the length of Manhattan. But it's time for the next project on our list. In the heart of Manitoba lies the Keeyask hydroelectric project, a marvel of engineering nestled along the Nelson River. Construction of the Keeyask project commenced in 2014, with a projected completion date of 2021. However, like many ambitious undertakings, the journey was fraught with challenges. The final cost of the project soared to approximately $8.7 billion, nearly double the initial estimate. This escalation stemmed from various factors, including unforeseen geological obstacles and environmental mitigation efforts. Spanning an area of over 23 square kilometers, the dam reaches a height of 23 meters and stretches over 640 meters in length. The construction process required a workforce of over 6,000 individuals, comprising skilled laborers, engineers, and environmental experts. These dedicated individuals braved the harsh Manitoba winters and navigated complex logistical challenges to bring this project to fruition. One of the key challenges faced during construction was the need to mitigate environmental impact. The project team implemented innovative solutions, including the construction of fish passages to ensure the continuity of fish migration routes and the preservation of local ecosystems. The Keeyask project integrates advanced technology to optimize power generation and distribution. The hydroelectric station boasts 6 generating units, capable of producing a combined output of 695 megawatts, enough to power approximately 400,000 homes. The electricity generated is transmitted through a network of transmission lines, connecting remote northern communities to the provincial grid. The completion of the Keeyask hydroelectric project marks a significant milestone in Canada's pursuit of renewable energy. For the next project, journey with us into the heart of Toronto, where the Eglinton Crosstown Light Rail Transit Project is reshaping the city's transit landscape. Spanning an ambitious 19 kilometers across Eglinton Avenue, the project was initiated in 2011 and completed in 2022. The project, budgeted at approximately $12 billion, underscores an epic saga of urban development, involving over 10,000 workers at its peak construction phases. The LRT line includes a significant underground section, spanning about 10 kilometers. Constructing this section involved the use of tunnel boring machines, each 10 meters in diameter. The scale of excavation is immense, with the project moving enough soil to fill the Rogers Centre twice over. One of the project's major challenges has been managing construction while minimizing disruption to one of Toronto's busiest arteries. Advanced technologies and construction methods, such as the cut and cover and sequential excavation method, have been employed to ensure the structural integrity of the cityscape and the safety of its bustling populace. Each of the 25 stations on the line presents its own unique architectural and functional features, designed to not only accommodate but also enhance passenger experience with art installations and technology. This project also tackles the pressing issue of urban congestion. By providing a reliable and efficient alternative to road transport, the Eglinton Crosstown LRT is expected to serve around 500 passengers per hour in each direction during peak times. Facing its fair share of hurdles, from labor strikes to engineering challenges due to the city's complex underground infrastructure, the project has navigated through delays and budget overruns, reflecting the all-too-common tale of large-scale urban transit projects. For our next project, we have to step into the bustling heart of British Columbia, where the Vancouver International Airport expansion is located. Launched in 2017, this expansive project was completed in 2022 with a cost of around 9.1 billion Canadian dollars. It's designed to accommodate the soaring passenger numbers, which are expected to reach 25 million annually by the end of the decade. This scale of growth brings its set of challenges and innovations, making the airport a focal point of Canadian aviation development. One of the most intriguing aspects of the expansion is the addition of a new international terminal wing. Spanning the length of nearly 3 Canadian football fields, the new wing is being built to handle the largest aircraft in the world. With 8 new gates, this terminal is not just large, but also a marvel of sustainability, designed to meet LEED Gold standards. The project also includes a massive upgrade to the airport's baggage handling system, increasing its capacity by 75%. This system will integrate cutting-edge technology to speed up baggage processing and improve the overall passenger experience. Construction at an operational airport presents the unique challenge of maintaining daily operations while minimizing disruption to passengers. The team has navigated these challenges through meticulous planning and phased construction, allowing the airport to remain fully functional as a key international hub. Comparatively, the scale of the airport's expansion is akin to adding a whole new airport the size of London City Airport right within its existing footprint. It's time to investigate the LNG Canada project next, which is a venture set to transform not only the landscape, but also the energy dynamics of the region. Initiated with a vision to tap into Canada's vast reserves of natural gas, the LNG project commenced in 2018 with an anticipated operational start by 2020. The project's grand scale is reflected in its $40 billion budget, making it the largest private sector investment in Canadian history. The ambition here is to liquefy natural gas efficiently and transport it across the globe, positioning Canada as a key player in the global energy market. The construction site itself spans over 400 hectares, equivalent to around 560 soccer fields combined. At the heart of the project are the advanced facilities designed to liquefy natural gas by cooling it to -162 degrees Celsius, transforming it into a liquid to reduce its volume nearly 600 times, making it easier and safer to store and ship overseas. The project's construction team employs cutting-edge construction techniques, including modular construction where large components are prefabricated elsewhere and assembled on-site, reducing construction time and environmental impact. The project is designed to achieve the lowest carbon intensity of any large-scale LNG plant in the world, utilizing renewable hydroelectric power for some of its processes, a significant departure from the more common reliance on fossil fuels for such operations. Challenges have been plentiful, ranging from logistical issues in transporting massive equipment through rugged terrain to navigating stringent environmental regulations that govern the preservation of the pristine northern British Columbia environment. We have to travel over to Alberta next for the Trans Mountain Pipeline Expansion Project next. Launched in 2017, this monumental project is designed to twin the existing pipeline, increasing the capacity from 300,000 to 890,000 barrels of oil per day, ensuring Canada's position as a leader in the global oil market. Spanning a staggering 150 kilometers, this pipeline cuts through mountains and rivers, connecting Alberta's rich oil fields to the world. The scale is immense, involving thousands of workers, each dedicated to meticulously constructing a route that respects both the environment and the communities it passes through. With a budget now estimated at 12.6 billion Canadian dollars, the project's costs have escalated due to rigorous environmental safeguards and the strategic implementation of cutting-edge construction technologies designed to minimize ecological impact. These methods include horizontal directional drilling, a technique that allows the pipeline to pass beneath sensitive ecological areas and major obstacles like the Fraser River without disturbing the surface. But the journey has not been without its hurdles. Navigating through one of the world's most rugged terrains, the project faces the relentless challenge of mountainous landscapes and the strictest environmental scrutiny. The line must also withstand the threats posed by seismic activity, demanding that every segment of the pipeline not only meets but exceeds safety standards. The expansion is more than just an engineering feat. It solves the critical problem of landlocked Alberta's oil market access. By providing a direct link to the Pacific coast, it opens up lucrative Asian markets, potentially increasing Canada's GDP by billions of dollars and ensuring thousands of jobs for Canadians for years to come. In terms of sheer volume, the amount of steel used in the pipeline is equivalent to building 60 Eiffel Towers. Next up, it's time for the Cinder Block project located in Ottawa. This extensive project aims to extend the life of the building for another century while updating it to meet contemporary standards of safety, accessibility, and functionality. Spanning over 500,000 square feet, the Cinder Block's overhaul is one of the largest heritage restoration projects in the world. In terms of interior upgrades, approximately 6,500 windows are being restored or replaced, and all mechanical and electrical systems are being completely overhauled to include state-of-the-art heating and information technology networks. These updates are critical in a building that must remain operational 24/7 and secure. The restoration also includes the removal and preservation of about 20,000 individual pieces of historically significant stonework. Each stone is bar-coded and tracked for restoration and exact replacement, utilizing both traditional stonemasonry techniques and advanced robotic cutting technology. Adding to the complexity, a new visitor welcome center is being constructed, which involves excavating nearly 50,000 cubic meters of bedrock equivalent to about 20 Olympic swimming pools. The project is expected to cost up to 5 billion Canadian dollars, a figure that reflects both the complexity of the work and the value placed on preserving a key element of Canada's national heritage. Environmental sustainability is a core component, with the project targeting LEED Gold certification through the use of sustainable materials and practices, including the maximization of natural light and the installation of energy-efficient systems that will reduce the building's carbon footprint. Welcome to the Port Mann Bridge, a towering marvel that stitches the sky over the Fraser River in British Columbia. Stretching over 10 lanes, the bridge spans an impressive 65 meters in width, which is almost as wide as 2 Olympic-sized swimming pools laid side by side. At its completion in 2012, it claimed the title of the longest cable-stayed bridge in North America, with a main span reaching 470 meters. The project wasn't just about setting up concrete and steel. It involved a meticulously orchestrated ballet of high-stakes engineering and logistics. Over 4,000 workers, each playing a pivotal role from welding to the precision placement of the 288 cables that support the massive span. These cables, if laid end-to-end, would stretch over 45 kilometers. The bridge was built to replace an older 5-lane bridge, addressing both the growing traffic needs and improving safety. The old bridge was frequently a choke point, snarling traffic and causing headaches for commuters. This new architectural giant not only doubled the number of lanes, but was designed to stand up to seismic events, a critical feature in the earthquake-prone Pacific Rim. But like any massive project, the Port Mann Bridge faced its share of challenges. Construction took place in a busy urban area, requiring intricate planning to minimize disruptions. Moreover, the project faced environmental concerns, particularly with its impact on the Fraser River's delicate ecosystem. Innovative solutions were applied, such as extensive water monitoring and careful timing of construction phases to protect local wildlife, especially the salmon runs. The cost of the bridge itself was a hefty $3.3 billion, part of a larger $2.46 billion highway improvement project, making it one of the most expensive infrastructure undertakings in Canada. In comparison to other megaprojects around the world, the Port Mann Bridge is a standout for its width and its advanced cable-stayed design, a technique also used in the famous Millau Viaduct in France, albeit on a grander scale. Let's travel over to the next project, called the Evergreen Line. When the Evergreen Line opened its doors to the public in December 2016, it wasn't just unveiling a new set of tracks. It was laying down 11 kilometers of advanced rapid transit that now serves as a critical spine, connecting over 70,000 passengers daily. This $1.43 billion project showcases the sheer scale and ambition of modern infrastructure endeavors, employing state-of-the-art construction methods and technology. Constructing the Evergreen Line involved laying enough track to stretch across about 100 football fields placed end to end. Within this sprawling network, 6 new stations emerged, each designed with unique architectural elements reflecting the character of their respective neighborhoods, enhancing not just functionality but also community identity. The construction of this project was a monumental task involving more than 8,000 workers who came together to tackle a variety of complex challenges. One of the most significant feats was the boring of a 2-kilometer tunnel beneath Burnaby Mountain, a technical marvel in itself. This tunnel, crucial for connecting the two ends of the line, required one of the largest earth pressure balance tunnel boring machines used in North America. The machine, nicknamed Alice, represents the spirit of innovation and determination that fueled this project. Dealing with the diverse terrain of the region, from dense urban areas to the delicate ecosystems surrounding the mountain, posed its own set of challenges. Engineers and planners meticulously designed the route and construction phases to minimize environmental impact, which included preserving the local creeks and surrounding green spaces. It's time to investigate the Oakridge Centre redevelopment in Vancouver, British Columbia. Embarking on its journey in 2019, this megaproject is slated for completion in phases, culminating in 2025. It's not just a facelift, but a complete overhaul of the 1955-era shopping mall into a vibrant, mixed-use community space. The scope is a staggering $5 billion investment that promises to redefine luxury and accessibility in urban development. The Oakridge Centre isn't just growing, it's being reinvented, set to encompass over 2.7 million square feet of retail and residential space combined. That's about the size of 47 football fields. Within this sprawling complex, there will be over 2,600 homes housing approximately 6,000 residents. The building's design includes cutting-edge sustainability features aiming for LEED Gold certification, which involves sophisticated water recycling systems and energy-efficient building practices. But as with any project of this magnitude, challenges are part of the story. The redevelopment must intertwine with the existing metro line, demanding precision and innovation to ensure seamless integration without disrupting daily commuter flows. Moreover, balancing the needs of current tenants with ongoing construction activities requires a symphony of logistical prowess. Oakridge's planned retail space alone will rival the size of the famed Mall of America in terms of square footage. It's time to move over to the next megaproject. Welcome to the Vimy Memorial Bridge, an engineering marvel stretching gracefully over the Rideau River in Ottawa, Ontario. This bridge was opened to the public in 2014, embodying a blend of historical significance and modern engineering. Diving into the details, the bridge spans an impressive 125 meters with a width of 42 meters. Its construction was a sophisticated operation involving the precise placement of enormous precast concrete girders, each carefully lifted by a 100-ton crane. This method not only ensured the structural integrity, but also highlighted the advanced techniques used in its design. A project of this magnitude required a substantial investment, with the budget reaching around $50 million. This funding was directed into various aspects of the construction, ensuring that the bridge was built to last and to handle the heavy traffic flow efficiently. More than 300 skilled workers contributed to the project, working diligently to meet the construction deadline and tackle any challenges that arose. The environmental impact was a significant concern given the bridge's location over a navigable waterway. Stringent measures were taken to protect the Rideau River's water quality and its surrounding ecosystems. In terms of materials, the bridge required about 6,000 cubic meters of concrete and 4,000 metric tons of structural steel, all carefully selected to ensure durability and aesthetic appeal. These materials were crucial in constructing a bridge that was not only functional, but also visually striking. What sets the Vimy Memorial Bridge apart is not just its functionality, but its commemorative nature. The bridge features a dedication plaque that includes soil from the actual Vimy Ridge battlefield in France, making it a living memorial that honors Canadian history while serving a practical purpose in modern-day Ottawa. Let's move over to the Spadina subway extension megaproject next, located in Toronto. Officially opened in December 2017, this project not only extended the western reach of the city's subway network, but also bridged the gap between Toronto and the York region, fostering an unprecedented level of accessibility across these bustling areas. The extension added 6 new stations along an 8.6-kilometer stretch, starting from Downsview Park all the way to the Vaughan Metropolitan Centre. The design and construction of these stations involved a collaboration among some of the world's most innovative architects and engineers, aimed at creating spaces that are not just transit nodes, but also community hubs. The budget for this expansive project was initially set at $2.6 billion, but saw an increase to nearly $3.2 billion due to various challenges and complexities encountered during construction. These challenges included engineering hurdles such as tunneling near existing infrastructure, managing underground water flows, and coordinating with multiple contractors and stakeholders to keep the project moving forward smoothly. One of the most significant engineering feats was the use of tunnel boring machines, which carved through the earth beneath the city with precision. These machines played a pivotal role in creating the 6.4-kilometer twin tunnels that form the backbone of the extension. The project not only expanded the physical landscape of Toronto's subway system, but also addressed crucial urban issues like congestion and sustainable urban growth. By providing a reliable and efficient public transit option, the extension has significantly reduced traffic volumes on the busy highways and main roads, leading to a more environmentally friendly and less congested urban environment. But we haven't talked about the Regina Bypass megaproject yet. Officially opened in October 2019, this bypass is not just a road. It's the largest transportation infrastructure project in the province's history, designed to streamline traffic and foster economic growth by improving access to the global transportation network. Spanning an impressive 61 kilometers, the Regina Bypass circles the city, from Highway 11 west of Regina through to Highway 1 east, providing a vital link for the heavy flow of trucks and local traffic. The construction of this mega project involved laying hundreds of thousands of tons of asphalt, enough to cover a 2-lane road stretching from Regina to Moose Jaw and back again. With a budget of approximately $1.9 billion, the project marked a significant investment in Saskatchewan's infrastructure. The bypass features 12 overpasses, 40 kilometers of new 4-lane highway, and 20 kilometers of resurfaced 4-lane highway. It also includes 55 kilometers of new service roads, offering a comprehensive network that enhances connectivity for local communities. Over 2,000 workers were involved in the construction, applying their skills across various aspects of the project, from earth moving and paving to bridge construction. This workforce was crucial in managing the 11 million cubic meters of earth moved during construction, an amount that could fill 4 Empire State Buildings. The project employed innovative construction techniques, including the installation of wildlife crossings to maintain natural habitats and migration patterns. Additionally, advanced engineering solutions were necessary to build the bypass in the challenging prairie landscape, often dealing with extreme weather conditions that required robust planning and adaptation. The Regina Bypass not only solves the problem of urban traffic congestion, but also significantly reduces travel time for freight transport, crucial for an agricultural hub like Regina. Special features of the project include innovative interchanges designed to handle large volumes of traffic efficiently, and the implementation of modern tolling technology to ensure ongoing maintenance and infrastructure funding without traditional toll booths. We have to move over to the Samuel de Champlain Bridge next. Spanning majestically over the St. Lawrence River, the bridge connects the island of Montreal with the South Shore in Quebec. This stunning piece of architecture, which officially opened in June 2019, stands as one of the largest infrastructure projects in North America and a pivotal gateway for the millions who traverse this corridor each year. The bridge stretches an impressive 3.4 kilometers in length, with a signature cable-stayed portion that reaches a height of 170 meters above the river. Designed not just for vehicular traffic, the bridge also accommodates a dedicated transit lane that will eventually support the REM light rail system. Building the Samuel de Champlain Bridge was a monumental endeavor, with a budget exceeding $4.4 billion. This project was essential to replace the aging original Champlain Bridge, which was one of Canada's busiest, carrying over 50 million vehicles annually. The old bridge was facing structural deterioration, posing a significant risk and necessitating the construction of a new, more durable structure. More than 2,000 workers were involved in the construction, utilizing innovative construction methods and materials to ensure longevity and durability. The bridge features a superstructure made from 74,000 tons of steel and 150,000 cubic meters of concrete. The construction faced significant challenges, particularly in managing the logistics of building in a busy urban area while minimizing disruptions to the existing traffic flows on the old bridge. Besides that, innovative techniques were employed to monitor and mitigate environmental impacts throughout construction. Comparatively, the scale and complexity of the Samuel de Champlain Bridge can be likened to San Francisco's Golden Gate Bridge in terms of iconic status and engineering marvel, though each unique in their structural expressions and utility. It's time to talk about the Quebec City Tramway project. This initiative reflects Quebec's commitment to sustainable mobility and is set to dramatically reshape how residents and tourists navigate the picturesque city. Projected to be operational by 2028, the tramway will stretch over 23 kilometers, featuring 23 stations and connecting major hubs like St. Foy and Charlesbourg to the heart of the old city. With a hefty budget estimated at over $3.3 billion, the tramway project is designed not only to enhance transportation, but to invigorate the local economy by improving accessibility to key commercial areas and reducing traffic congestion. The plan includes low-floor tram vehicles capable of enduring the city's challenging winter conditions, showcasing advanced engineering that prioritizes reliability and efficiency. Construction of the tramway involves laying tracks that will weave through densely populated neighborhoods and historic areas, requiring meticulous planning to preserve the integrity and heritage of the cityscape. This project is not without its problems. The construction phase has to address the city's unique topography and cold climate, which can significantly complicate excavation and construction activities. Special techniques are being used to minimize disruption to the daily lives of thousands of residents and to protect the architectural heritage for which Quebec City is famous. In terms of scale, the tramway's reach and impact are comparable to major transit projects like the Portland streetcar in Oregon, although Quebec's version is specifically tailored to meet the demands of a city known for its steep hills and historic architecture. The tramway will use a combination of at-grade and elevated tracks, strategically designed to blend with the surrounding environment while providing unobstructed views of the city's landmarks. Another innovative aspect of the Quebec City Tramway is its environmental focus. The project aims for a significant reduction in greenhouse gas emissions by promoting public transit over car use. The tram cars themselves are designed to be energy efficient and are expected to operate entirely on hydroelectric power, reflecting Quebec's abundant hydroelectric resources and commitment to renewable energy. The tramway is poised to solve several urban mobility issues, offering a reliable and eco-friendly alternative to car travel, thus enhancing the quality of life for residents and enriching the experience for tourists.
It's time for a much more expensive mega project next, located in the United Arab Emirates. Dubailand is an ambitious $64 billion mega development that aims to position Dubai as a global hub for tourism, entertainment, and luxury living. This project was first announced in October 2003 and is variously referred to as the Disneyland of the Middle East. Spanning over 278 square kilometers, Dubailand is designed to be one of the largest entertainment complexes in the world. The project spans 107 square miles inland from Palm Jumeirah, between Sheikh Mohammed bin Zayed Road and the desert. The development includes themed communities, attractions, and a variety of lifestyle options for residents and visitors. There are 50 visitor attractions spread over 26 development projects in the master plan. The biggest 4 projects are the themed residential communities: Arabian Ranches, Dubai Sports City, Falcon City of Wonders, and Gulf City. These areas offer affordable housing, family-friendly amenities, and peaceful surroundings. Newer developments like Talal Al Ghaf and Arabian Ranches II continue to add value to the area. Dubailand offers entertainment options for all ages. Dubai Sports City is a hub for sports enthusiasts with its cricket stadium, motor racing track, and Olympic-level facilities. It also hosts several sports academies, making it a top choice for families with active lifestyles. The community also includes gyms, swimming pools, and spas. Global Village is another popular attraction. This cultural event runs from October to April each year and features pavilions from over 100 countries. Visitors can enjoy live performances, unique shopping experiences, and delicious food from around the world. IMG Worlds of Adventure, one of the largest indoor theme parks in Dubai, offers thrilling rides and family entertainment. Dubailand is also home to many green spaces. The planned 350-acre public park will provide walking trails, playgrounds, and open areas for relaxation. Communities like Al Barari and the villas focus on eco-friendly living and tranquility. Golf enthusiasts can practice their skills on championship courses in Arabian Ranches. Future expansions include DreamWorks-themed parks and additional cultural and recreational zones. Once fully developed in the upcoming few years, Dubailand is expected to draw millions of visitors annually. Dubailand utilizes prefabrication techniques for its extensive theme park structures, high-capacity tower cranes for skyscrapers, and automated earth-moving machinery for landscaping. Virtual reality modeling aids in design accuracy, while robots are employed for intricate tasks like painting and facade installation on high-rises. While Dubailand offers a peaceful alternative to central Dubai, it is still developing. Residents enjoy lower traffic, affordable rents, and many nearby schools and shops. However, commuting often requires a car due to the spread-out layout. Next up, we have to talk about the $119 billion New York City seawall project, an ambitious response to rising sea levels and increasing storm surges. Known as the Big U, this protective infrastructure aims to shield the city from the devastating effects of climate change. The devastating impact of Hurricane Sandy in 2012 underscored the vulnerability of the city to extreme weather events, with over $70 billion in damages. In response, the U.S. Army Corps of Engineers developed the New York Harbor Storm Surge Barrier Plan. The seawall will stretch approximately 6 miles along the coastline, acting as a barrier to shield New York Harbor and Lower Manhattan from extreme weather events. This ambitious project will storm gates, levees, and natural wetlands restoration to absorb water and reduce storm impact. This 20-foot tall seawall is part of a $10 billion plan to climate-proof New York City. It will include a public walkway that can host events like concerts and marathons. Building a seawall of this magnitude requires advanced engineering to ensure resilience against powerful storms and rising tides. Engineers are using a combination of reinforced concrete and steel structures to construct the barrier. Deep foundation piles are driven into the seabed to anchor the wall securely. The project also integrates movable storm gates, which can close during severe weather and reopen for normal maritime traffic. Hydrodynamic modeling and simulations were conducted to optimize the design and placement of walls. Advanced modeling techniques, including AI-based simulations, have been employed to predict storm behavior and optimize barrier placement. The wall incorporates tidal gates to maintain water flow and preserve the ecological balance of the harbour. Some sections feature living shorelines, blending natural habitats with engineered defences to promote biodiversity and reduce wave energy. The project involves dredging, reinforced piling, and innovative materials resistant to erosion and saltwater corrosion. Despite the staggering cost of $119 billion, the seawall is projected to save over $200 billion in potential damages. Once completed, the seawall will protect New York City from catastrophic flooding and redefine urban waterfront living.
The Northconnect tunnel in Sydney, Australia, completed in 2020, is a critical infrastructure project designed to alleviate traffic congestion and improve connectivity between the M1 Pacific Motorway and the M2 Hills Motorway. This 5.6 twin tunnel project involved several innovative engineering techniques and addressed various challenges posed by the urban environment. The construction of the Northconnect tunnel began with the excavation of deep access shafts, providing entry points for tunnel boring machines. These machines were specially designed to excavate through the sandstone and shale prevalent in the region. Each TBM, over 470 feet long, used rotating cutter heads to grind through the rock, creating the tunnel bore. The excavated material was transported out of the tunnel using conveyor belts and hoisted to the surface through the access shafts. The tunnel lining was constructed using precast concrete segments, which were installed by the TBMs as they advanced. These segments, designed to withstand the high pressure at depth, were bolted together to form a watertight lining. The use of precast segments allowed for rapid construction and high-quality control, ensuring the structural integrity of the tunnels. One of the primary engineering challenges was managing the ventilation and safety systems required for a long tunnel. The Northconnect tunnel features a state-of-the-art ventilation system, including jet fans and exhaust stacks, designed to maintain air quality and manage smoke in the event of a fire. The ventilation system is controlled by an advanced monitoring system, which adjusts airflow based on real-time conditions within the tunnel. The construction also included the development of large portal structures at the tunnel entrances, designed to integrate with the existing road network. These structures required extensive earthworks and construction of retaining walls and embankments to support the elevated roadways. The portal structures were designed to provide smooth transitions and minimize disruptions to traffic flow. The Northconnect tunnel project showcases the application of advanced tunneling technology and engineering practices to address critical infrastructure needs. The project significantly reduces traffic congestion, improving travel times and road safety in Sydney. The construction of this extensive tunnel network demonstrates the capabilities of modern engineering to solve complex urban infrastructure challenges.
But just wait until you hear about one of China's most expensive projects, the South-North Water Transfer Project, with $79 billion already spent. This Chinese megaproject addresses the critical water scarcity issues in the country by transferring water from the resource-rich south to the drought-prone north. The project includes three main routes: the eastern, central, and western lines. The eastern and central routes are operational, supplying water to cities like Beijing, Tianjin, and Shandong province. The western route, still in planning, aims to divert water from the upper reaches of the Yangtze River through the Tibetan Plateau to northern provinces. Spanning over 2,000 kilometers, the project required constructing massive canals, tunnels, pumping stations, and reservoirs. The central route alone diverts 9.5 billion cubic meters of water annually and passes through engineering feats like the Danjiangkou Reservoir. The project is complex and uses TBMs for tunneling, hydraulic drilling machines for dam construction, and high-capacity pumps for testing canal systems. Precision-guided excavators handle massive earth-moving tasks, while automated concrete pouring systems ensure uniformity in canal linings. Advanced monitoring devices are employed to maintain water flow integrity. Due to the topography of the Yangtze Plain and the North China Plain, pumping stations will be employed. They'll raise water from the Yangtze to the Yellow River crossing. Farther north, the water will flow downhill in an aqueduct. The project has brought much-needed water to arid regions, supporting agriculture, industry, and urban growth. By securing water resources for northern economic hubs in China, the project sustains industrial output, urbanization, and population growth. It also reduces reliance on overexploited groundwater, preventing further environmental degradation. Despite its successes, the project has faced significant challenges. Relocation of over 330,000 people to create reservoirs sparked social concerns. Additionally, managing pollution along the routes remains a priority, as water quality directly impacts urban and agricultural usage. Scientists have expressed concerns that the project could increase water evaporation loss. The exact amount of evaporation loss is not known, but it may improve in the future as more water is transferred and the flow rate increases. With more than 40 billion cubic meters of water transferred annually, the project is a lifeline for many regions. Its completion in 2050 will mark a significant milestone in global water management, demonstrating how large-scale infrastructure can address critical resource challenges. But have you ever heard about the remarkable Spiral Tower? Rising 1041 feet above Hudson Yards in Manhattan, the Spiral is a $3.7 billion skyscraper that redefines sustainable and innovative architecture. The Spiral was conceived as a mixed-use development offering office spaces, retail, and public amenities. Its name comes from the cascading terraces that spiral around the building, creating a continuous ribbon of green spaces from top to bottom. This unique feature connects all floors with landscape terraces, symbolizing an architectural evolution toward greener urban environments. The tower provides 2.85 million square feet of office space and luxurious amenities. A striking feature is its 66th floor, open-air terrace and clubhouse, offering panoramic views of the city. The interiors seamlessly blend modern aesthetics with functionality, creating an atmosphere of sophistication. Its facade features high-performance glazing to maximize natural light while minimizing heat gain, contributing to energy efficiency. The advanced irrigation system conserves 4.5 million gallons of water annually compared to traditional systems. Its construction involved modular building techniques, accelerating the assembly of its complex design. Steel and concrete were the primary materials, ensuring structural integrity while accommodating its unique spiraling terraces. Prefabricated components were brought to the site and assembled with millimeter precision, reducing construction time and waste. To ensure stability, engineers implemented an advanced core and outrigger system, which provides resistance against wind forces and seismic activity. The building also features rainwater collection systems integrated into the terraces, enabling irrigation for the lush greenery. The Spiral incorporates cutting-edge sustainable technologies. Its green terraces improve air quality and reduce urban heat, while smart systems monitor and optimize energy use in real time. The building also includes advanced HVAC systems and water-efficient plumbing, reducing its environmental footprint.
The new Manila International Airport in the Philippines is an ambitious project designed to alleviate congestion at the existing Ninoy Aquino International Airport. Scheduled for completion in phases with full completion expected by 2025, this airport will feature 4 parallel runways and a capacity to handle 100 million passengers annually. The construction involves massive earthworks, advanced engineering techniques, and meticulous planning to create a state-of-the-art facility. The initial stages of construction focused on land reclamation and site preparation, as the airport is being built on a low-lying area prone to flooding. To address this, engineers employed a combination of dredging and soil stabilization techniques. millions of cubic meters of sand and fill material were dredged from nearby areas and transported to the site, raising the ground level and creating a stable foundation for the airport infrastructure. The use of geotextiles and ground improvement techniques, such as dynamic compaction and prefabricated vertical drains, helped to accelerate the consolidation of the reclaimed land and improve its load-bearing capacity. The construction of the airport's runways involved precise grading and paving techniques to ensure smooth and durable surfaces. Each runway is designed to accommodate the largest commercial aircraft, requiring layers of high-strength asphalt and concrete. The paving process utilized advanced machinery and techniques, including slip-form pavers and laser-guided screeds, to achieve the required surface smoothness and thickness. The terminal buildings, designed to handle the high-pressure volume, incorporate modern architectural and engineering principles. The construction of these structures involves the use of prefabricated steel components and modular construction techniques, which allow for rapid assembly and high-quality finishes. The terminal roofs are supported by a network of steel trusses, creating large open spaces that enhance passenger comfort and flow. One of the significant challenges of the New Manila International Airport is integrating advanced technological systems. The airport will feature state-of-the-art air traffic control systems, automated baggage handling, and advanced security screening technologies. The installation and integration of these systems require careful coordination between different contractors and suppliers, ensuring that all components work seamlessly together to provide a safe and efficient airport operation.
Next, we have to talk about the impressive Solidarity Transport Hub, transforming Poland into a key transportation hub for Europe. Located between Warsaw and Łódź, this $8 billion greenfield airport is set to have a transformative impact on regional connectivity, security, and economic growth. Chapman Taylor created a concept design for the proposed new Central Transportation Hub. The concept envisions a 6-level structure called Solidarity Transport Hub, which will offer a new template for transport interchanges. The design of the internal hierarchy is inspired by the 6 main landscapes of Poland: Baltic coast, Lake District, valleys, uplands, plains, and mountains. The focus of the hub is a circular dome symbolizing the unity of Poland and the connectivity at the heart of this concept. The 37 square kilometer site spans the municipalities of Baranów, Terezin, and Łyskitki. It lies conveniently near the A2 motorway, offering swift access to key urban centers. The project also includes over 1,600 kilometers of new railway lines. This will enable passengers to reach Warsaw in just 15 minutes and connect to major Polish cities in under 2.5 hours. This integrated transport model promises unparalleled efficiency for commuters and travelers. Scheduled to open by 2028, the airport will initially accommodate 40 million passengers annually, with plans to expand capacity in the future. The hub will feature dual-use capabilities, serving both civilian and military needs. This vision underscores its importance beyond commercial aviation. The construction plans are equally ambitious. In 2023, preliminary groundwork began with tasks such as tree removal, site leveling, and the establishment of temporary structures. Tunnel boring machines are employed for underground rail networks, while high-precision cranes are operational for assembling airport terminals. Heavy earth-moving equipment like bulldozers and excavators handle large-scale groundwork, while automated machinery ensures precise rail track alignment. Sustainability is a cornerstone of the airport project. Its design incorporates eco-friendly technologies and aims to minimize environmental impact. The tempered dome will reduce energy loads traditionally associated with this type of development. The rail and aviation functions will be seamlessly integrated for easy travel. The dome will create a flexible, weatherproofed environment that allows cost-effective evolution over time, as required. The integration of renewable energy sources and efficient waste management systems will further enhance its green credentials. The hub is expected to boost Poland's GDP by attracting investments, enhancing tourism, and generating over 15,000 jobs. Strategically, it will strengthen Poland's position as a key player in the European Union and a bridge between Western and Eastern Europe. But just wait until you hear about the Buffalo Bills Stadium, officially named Highmark Stadium. Located in Orchard Park, New York, the project aims to give fans an unparalleled game day experience while boosting regional pride. The original Highmark Stadium, built in 1973, has served as the home for the Buffalo Bills for 5 decades. However, the aging structure no longer meets the demands of modern football or fans. In response, a new $1.5 billion project was approved in 2022, marking the largest investment in Buffalo sports history. The new Buffalo Bills Stadium will cover 1.35 million square feet with a seating capacity of 6,000 talents. It will feature a partial canopy roof to protect fans from Buffalo's unpredictable weather while maintaining an open-air field to preserve the essence of outdoor football. The design includes state-of-the-art amenities like advanced video boards, immersive sound systems, and expansive concourse areas. Enhanced VIP suites, fan zones, and technology-driven experiences aim to elevate spectator engagement. Construction began in early 2023 and is set to complete by the 2026 NFL season. The project uses modular construction techniques, allowing for faster assembly and better quality control. High-strength steel and precast concrete ensure the structure's durability and safety. One of the most impressive aspects of the stadium is the canopy structure. Engineers are using high-strength steel and tension cables to create a lightweight yet durable canopy system. This design minimizes obstructions, ensuring clear sightlines for fans while withstanding harsh weather conditions, including heavy snow and high winds. The foundation of the stadium required extensive excavation and reinforcement to accommodate the weight of the canopy and ensure long-term stability. Advanced drainage systems are being installed to handle Buffalo's frequent rainfall and prevent water damage to the structure. Prefabrication techniques are being used to speed up construction. Components of the canopy and seating sections are manufactured off-site and assembled on-site, reducing costs and construction time. The stadium incorporates sustainable practices, such as energy-efficient systems and rainwater harvesting. Materials are sourced locally to minimize environmental impact, aligning with Buffalo's commitment to green development. The project is expected to create 10,000 jobs during construction and inject millions into the local economy. Once completed, the stadium will host NFL games, concerts, and events, making it a year-round hub for activity and revenue.
The Dig Indy Tunnel System in Indianapolis, United States, is an extensive network of deep rock tunnels designed to reduce sewer overflows into local waterways. Scheduled for completion in 2025, this project involves the construction of over 28 miles of tunnels, each approximately 18 feet in diameter and located 250 feet below ground. The construction process began with the excavation of deep access shafts, providing entry points for tunnel boring machines. These TBMs were specially designed to excavate through the limestone bedrock prevalent in the region. The TBMs, each over 300 feet long, used rotating cutter heads to grind through the rock, creating the tunnel bore. The excavated material was transported out of the tunnel using conveyor belts and hoisted to the surface through the access shafts. The tunnel lining was constructed using precast concrete segments, which were installed by the TBMs as they advanced. These segments, designed to withstand the high pressures at depth, were bolted together to form a watertight lining. The use of precast segments allowed for rapid construction and high-quality control, ensuring the structural integrity of the tunnels. One of the primary engineering challenges was managing groundwater infiltration. The tunnels were designed with a comprehensive dewatering system, including pumps and drainage galleries to control groundwater levels and prevent flooding. Additionally, the tunnel lining included waterproof gaskets and grout injection systems to seal any potential leaks. The Dig-Indy tunnel system also involved the construction of a large storage and conveyance structures designed to hold and transport combined sewer overflows during heavy rainfall events. These structures were integrated with the existing sewer network, requiring extensive coordination and planning. The project included the installation of advanced control systems, allowing for real-time monitoring and management of these sewer flows. The Dig-Indy Tunnel System project showcases the application of advanced tunneling technology and engineering practices to address critical infrastructure needs. The project significantly reduces sewer overflows, improving water quality and public health in Indianapolis. The construction of this extensive tunnel network demonstrates the capabilities of modern engineering to solve complex urban infrastructure challenges.
But we have to talk about one of the most expensive mega projects ever constructed in France. The Grand Paris Express is an impressive infrastructure project reshaping transportation in the Paris metropolitan area. It is the largest metro expansion project in Europe, designed to modernize the transit network and promote sustainable urban growth in Paris. With an estimated cost of $45 billion, the Grand Paris Express is expected to address the growing population and commuter needs. The project involves constructing 200 kilometers of new rail lines and 68 stations, significantly improving connectivity across the Île-de-France region. It introduces 4 entirely new metro lines while extending existing lines to connect previously underserved suburbs directly. These additions aim to link neighborhoods without requiring travel through central Paris, cutting travel times drastically. For example, a trip that might take over an hour today will take only 30 minutes or less once the network is operational. The heart of the project is Line 15, a circular route connecting key areas like Saint-Denis, La Défense, and the southern and eastern suburbs. The trains will be driverless, offering increased safety, reliability, and efficiency. The network also emphasizes environmental sustainability. Powered by renewable energy, the system is expected to reduce road traffic and decrease greenhouse gas emissions significantly. Stations for the Grand Paris Express are just as remarkable. The Saint-Maur-Créteil station, at 52 meters below ground, will be the deepest in France. Construction of the Grand Paris Express employs advanced techniques and massive machinery. It involves creating reinforced waterproof walls and excavating 60-meter deep boxes. The internal structures, including platforms and mezzanines, are built afterward, combining function and architectural excellence. The scale of construction is enormous. Tunnel boring machines, over 100 meters long, excavate tunnels 30 to 40 meters deep beneath Paris. These machines advance at a rate of 12 meters per day, leaving behind completed tunnels lined with concrete. This engineering feat avoids the dense web of underground utilities accumulated over a century, ensuring minimal disruption. The project incorporates cutting-edge technology. Field surveys and tunnel measurements rely on advanced software like Trimble, ensuring precision and efficiency. This digital integration allows teams to manage vast amounts of data, enabling smooth collaboration and faster timelines. Construction of the Grand Paris Express began in 2015 and is expected to finish by 2030. The project aims to remove 150,000 vehicles from the streets, significantly reducing carbon emissions. By improving public transport, it supports the city's goal of cutting 27.6 million tons of carbon emissions by 2050. Next up, we have to talk about an $8 billion plan to save LaGuardia Airport, one of the largest airport reconstruction projects in history. Once criticized for its outdated infrastructure and passenger experience, LaGuardia is now undergoing a complete transformation. This modernization project involves constructing entirely new terminals, upgrading runways, and improving accessibility. The key components include a state-of-the-art Terminal B, a new Terminal C for Delta Airlines, and a central arrivals and departures hall that connects all terminals seamlessly. The state-of-the-art facility at LaGuardia will span 1.3 million square feet, featuring 37 gates across 4 concourses. There's also a direct-to-security luggage drop-off option. Passengers will enjoy security features, improved transportation access, additional taxiways to reduce delays, iconic public art, gourmet food offerings, and more. The restrooms have corridors behind them, so janitors can empty the trash without disturbing customers. The entrances have mosaic murals representing different parts of New York City. One of the standout features of the terminal is its aquagraphic water curtains integrated into the design of the terminal. These curtains, located on the 4th level of the arrivals and departures hall, create a mesmerizing visual experience by using 450 solenoid valves, manipulating water into precise, figurative, and abstract forms. The water ballet is synchronized with light projections and video displays, turning the airport into an artistic space for travelers. The project involves demolishing existing structures and replacing them with state-of-the-art terminals, such as the newly completed Terminal B. Modular construction methods have been used to minimize disruptions to airport operations. The new terminals feature large-span steel trusses, allowing for open, airy interiors without compromising structural integrity. A signature pedestrian bridge connecting Terminal B to 2 concourses was built using prefabricated sections. Modern baggage handling systems and smart technology have been integrated to improve efficiency and reduce wait times. The project also includes enhanced transportation links to and from the airport, the improved connections to the New York City subway system, and a dedicated bus terminal make LaGuardia more accessible to travelers across the city. The new design will also focus on sustainability, with the integration of energy-efficient systems and eco-friendly materials throughout the airport. The renovation will add state-of-the-art security features, expanded concourses, and more comfortable seating areas for travelers. The new LaGuardia will be able to handle 30 million passengers annually by 2025.
The Silvertown Tunnel in London, scheduled for completion in 2025, is a twin-bore road tunnel under the River Thames connecting the Greenwich Peninsula to the Royal Docks. This ambitious project employs state-of-the-art tunnel boring machines, each over 82 feet long and weighing approximately 1,350 tons, designed to handle the challenging geological conditions beneath the Thames, including water-bearing gravels and stiff clays. Construction began with the sinking of deep shafts on both sides of the river. These shafts provided the starting points for the TBMs and will eventually house the tunnel portals. The TBMs, named after historical figures, are equipped with rotating cutter heads that excavate soil and rock, which is then transported out of the tunnel via conveyor belts. The TBMs advance at a rate of around 33 feet per day, lining the tunnel with precast concrete segments as they progress. These segments are bolted together to form a watertight lining, ensuring the structural integrity of the tunnel. One of the primary engineering challenges of the Silvertown Tunnel project is maintaining the stability of the tunnel and preventing groundwater filtration. The construction site is located in a densely populated urban area with significant historical and environmental considerations. To mitigate this, extensive geotechnical surveys and advanced 3D modeling techniques were conducted to ensure the tunnel's stability and integrity. The tunnel is designed to accommodate both current and future traffic demands, with each bore containing 2 lanes and provisioning for future expansion. The alignment of the tunnel was meticulously planned to avoid existing underground utilities and infrastructure, requiring detailed geotechnical surveys and advanced 3D modeling techniques. This planning ensures that the tunnel can be integrated seamlessly into existing road networks, minimizing the need for extensive surface work and disruptions. To enhance the safety and efficiency of the construction process, the project utilizes Building Information Modeling technology. BIM allows for the detailed planning and simulation of construction activities, helping to identify potential issues before they arise and streamlining the construction process. This technology also facilitates collaboration between different teams and stakeholders, ensuring that the project remains on schedule and within budget.
Next up, we have to talk about the Sangley Point International Airport Megaproject in the Philippines. Located in Manila Bay, Cavite, this $11 billion project seeks to address the growing demand for aviation infrastructure while tapping into the strategic location of Sangley Point. Initially designed to streamline the Ninoy Aquino International Airport, the airport aims to be a useful addition to the existing transport network. Construction of the first runway began in 2024, with a targeted completion in 4 years. Once operational, it will accommodate 25 million passengers annually. There's a second runway planned to expand the capacity to an impressive 75 million passengers. The design of Sangley Point International Airport incorporates cutting-edge engineering and technology to optimize functionality and passenger experience. It will include state-of-the-art terminals, cargo facilities, and a dedicated area for private jets. The design integrates advanced technology for seamless passenger and cargo handling, reducing delays and boosting efficiency. Its location on Manila Bay necessitates extensive groundwork to address environmental and geographical challenges. Advanced reclamation techniques will be employed to stabilize the site, while state-of-the-art drainage systems will mitigate the risk of flooding. The runway construction will use durable, weather-resistant materials to ensure longevity and operational reliability. The project uses dredges to reclaim land from Manila Bay, heavy-duty cranes for erecting terminal structures, and asphalt pavers for runway construction. Advanced piling rigs ensure stable foundations in reclaimed areas. Modular construction techniques speed up building processes, while automated equipment handles material transportation. There's an alternative vision for Sangley that focuses on its potential as a logistics hub and free port. Drawing inspiration from the successful redevelopment of Subic Bay and Clark, authorities suggest repurposing Sangley to complement the growing trade and industrial sectors. Its proximity to the Cavite Export Processing Zone and the Calabazon Industrial Belt positions it as an ideal center for logistics and air-sea integration. The shift toward e-commerce and fast-paced global supply chains underscores the need for dedicated logistics infrastructure. A logistics-focused Sangley could relieve the cargo burden on NAIA, offering streamlined operations for air freight and shipping. This dual-purpose model could also preserve military history in Sangley, allowing for the coexistence of defense and commerce. Sangley Point is expected to generate thousands of jobs during construction and operational phases, bolstering the local economy. By increasing aviation capacity, the airport will enhance tourism and trade, two critical sectors for the Philippines. The first phase is expected to be operational by 2028. Once complete, Sangley Point International Airport will ease travel for millions and support economic growth. Next, we have to talk about the incredible Central Park Tower, soaring 1,550 feet above New York City. This tower holds the title of the tallest residential building in the world. Located on Billionaires Row along West 57th Street, this architectural marvel represents luxury and engineering mastery. Completed in 2020, it redefines urban living while contributing to the iconic Manhattan skyline. Its construction began in 2014 with the goal of combining cutting-edge engineering with luxury. The prime location of the tower offers unparalleled views of Central Park and beyond, making it a coveted address for the world's elite. With a total cost of approximately $3 billion, the building houses 179 ultra-luxurious residences, including a triplex penthouse, along with premium commercial spaces. Residents enjoy access to the Central Park Club, a 3-story private club featuring a ballroom, outdoor terrace, and a 60-foot swimming pool. Other amenities include a state-of-the-art fitness center, private dining spaces, and unparalleled views of Central Park. While luxury is its hallmark, Central Park Tower incorporates sustainable features. High-performance glass reduces energy consumption by optimizing natural light while minimizing heat gain. Efficient HVAC systems and LED lighting further enhance energy efficiency. Central Park Tower stands 98 stories tall with a unique cantilever design that extends over neighboring structures to maximize views. The exterior features a sleek curtain wall facade made of reflective glass and stainless steel, enhancing its modern aesthetic. The structure employs a concrete and steel core to ensure stability and withstand high wind pressures, a necessity for super tall skyscrapers. Advanced damping systems minimize swaying, ensuring comfort for residents on higher floors. The interiors of the tower reflect sophistication, with premium materials like marble, custom woodwork, and high-end fixtures. Residents also enjoy exclusive amenities spread across 5,000 square feet, including a private club, fitness center, spa, and a 60-foot indoor pool. Building a skyscraper of this scale posed significant challenges, including navigating strict zoning regulations in New York and coordinating complex logistics in a densely populated area. Modular construction techniques and a high-strength concrete mix were employed to expedite the process. Workers meticulously assembled the cantilevered sections of the building to ensure structural integrity without compromising aesthetic appeal.
The Red Line Doha Tunnel in Qatar is a key component of the Doha Metro network, designed to provide efficient and reliable public transportation. The construction of this 25-mile-long tunnel, completed in 2019, involved several engineering and logistical challenges, particularly given the region's geological conditions. The tunnel was constructed using tunnel boring machines, which are highly specialized for excavating through the soft rock and soil conditions prevalent in Doha. Each TBM was over 328 feet long and weighed approximately 1,200 tons. These machines were equipped with rotating cutter heads that excavated the soil and rock, which was then transported out of the tunnel using conveyor belts. The construction also involved the careful monitoring and management of ground settlement, particularly in urban areas. Advanced geotechnical instruments such as inclinometers and extensometers were installed to monitor ground movements and ensure the tunnel's stability. This real-time data allowed engineers to adjust construction methods and implement corrective measures as needed, minimizing the impact on existing buildings and infrastructure. The Red Line Doha Tunnel features a dual-track system, allowing for high-frequency train services. The tunnel is equipped with state-of-the-art systems for ventilation, lighting, and emergency evacuation. The ventilation system is designed to maintain air quality and manage smoke in the event of a fire, ensuring passenger safety. The construction process also included the development of underground stations, which required extensive excavation and support systems. These stations were designed with large open spaces to accommodate passenger flow and provide a comfortable environment. The use of advanced structural engineering techniques, such as diaphragm walls and deep foundation piles, ensured the stability and durability of these underground structures. The Red Line Doha Tunnel project showcases the application of advanced tunneling technology and engineering practices to create a modern, efficient, and resilient public transportation system. The project addresses the growing demand for sustainable transportation solutions in Doha, providing a reliable and high-capacity metro network that supports the city's development and connectivity.
Jubail 2 is an $11 billion industrial megaproject in Saudi Arabia, designed to expand the Jubail Industrial City, already the largest industrial complex in the world. The project is part of Saudi Arabia's Vision 2030 strategy to diversify the economy and reduce reliance on oil revenues. This mega project involves the development of 6,200 hectares of industrial land and the construction of state-of-the-art facilities for petrochemicals, refining, and other heavy industries. It includes new ports, roads, and residential areas to accommodate a growing workforce. The expansion adds world-class petrochemical plants, desalination facilities, and power stations. The Ras Al Khair Industrial City, part of Jubail 2, focuses on aluminum and phosphate industries, adding to Saudi Arabia's position as a global leader in non-oil sectors. The project incorporates sustainable practices, such as energy-efficient industrial processes and the use of desalination to meet water demands. It also leverages advanced technologies to optimize production and reduce environmental impact. Plasham Park is a cutting-edge industrial zone within Jubail 2. Plasham is designed to produce innovative products never before manufactured in the Middle East. It complements the Sadara Chemical Company, a $20 billion joint venture between Saudi Aramco and Dow Chemical. Sadara, completed last year, consists of 26 units that produce over 3 million tons of products annually. Together, these facilities are expected to contribute billions annually to Saudi Arabia's GDP. Sadara is already employing nearly 5,000 people, while Plasham is set to create up to 20,000 jobs over the next decade. This ambitious industrial park will see $5.7 billion in investment, hosting dozens of new factories. In the future, Plasham Park will connect to the regional transport network, linking Ras Al Khair to Dammam via a railway line, ensuring smooth logistical operations. But the significance of Jubail 2 extends beyond Plasham. It is home to the Saudi Aramco Total Refining and Petrochemical Company, SATORP, a facility processing 400,000 barrels per day. Developed by the Royal Commission for Jubail and Yanbu, this expansion has made Jubail the largest industrial hub in the region. Jubail 2 relies on heavy-duty dredgers for port construction, high-capacity cranes for industrial facilities, and robotic welders for pipeline assembly. Modular construction techniques are employed for the rapid building of residential areas, while GPS-enabled equipment ensures precision in infrastructure alignment. Desalination plants use advanced reverse osmosis machinery. Coordinating large-scale construction, infrastructure, and industrial operations has posed logistical challenges. Despite this, significant milestones have been achieved, with further phases set for completion by 2030. Let's move over to the One Vanderbilt, which was completed in 2020 and redefined the New York City skyline as a towering example of engineering brilliance. Located adjacent to Grand Central Terminal, this $3.3 billion skyscraper is a symbol of innovation and sustainability, merging functionality with breathtaking design. The project was conceived in 2010 as part of Midtown East's rezoning plan, aimed at revitalizing the area. Construction began in 2016, with the goal of creating a state-of-the-art commercial hub that integrates seamlessly with public transit systems. One Vanderbilt stands at 1,401 feet, making it the fourth tallest building in New York City. It offers 1.7 million square feet of office space spread over 58 stories, designed to accommodate thousands of workers. The tower features Summit One Vanderbilt, an immersive observation deck at 10 feet, providing panoramic views of the city. Advanced elevator systems reduce wait times, enhancing efficiency. The construction of One Vanderbilt presented significant challenges due to its proximity to Grand Central Terminal. Engineers had to ensure the tower's foundation did not disrupt the historic infrastructure beneath. To achieve this, they used drilled caissons to transfer the building's weight deep into the bedrock, ensuring stability. The structure incorporates a steel and concrete hybrid frame, providing the strength needed to withstand wind forces at such heights. Engineers also designed the building with tapered setbacks, reducing wind loads and giving the tower its iconic shape. A tuned mass damper, weighing hundreds of tons, is installed near the top to counteract swaying and enhance comfort for occupants. Modular construction accelerated timelines while maintaining quality. Its glass curtain wall facade minimizes heat gain while maximizing natural light, contributing to energy efficiency. Integration with Grand Central Terminal involved building a direct transit connection, allowing seamless access to subway and commuter trains. This made One Vanderbilt a central transit-oriented development. The $3.3 billion project not only transformed Midtown Manhattan, but also generated thousands of construction jobs.
The Captain Cook Bridge in Brisbane, Australia, completed in 1972, is a significant construction project that spans the Brisbane River, connecting the southern suburbs to the central business district. The bridge's construction involved several innovative engineering techniques and addressed various challenges posed by the river's width and tidal fluctuations. The bridge is a pre-stressed concrete structure consisting of a continuous box girder design. The construction process began with the sinking of deep caissons into the riverbed to provide stable foundations for the bridge piers. These caissons, large cylindrical structures, were constructed using reinforced concrete and driven into the riverbed using pile drive equipment. Once in place, they were filled with concrete to create solid footings for the bridge. The box girder sections were precast in segments on shore and then transported to the construction site using barges. These segments were assembled using the balanced cantilever method, where sections were added symmetrically on either side of the piers. This method ensured that the structure remained balanced and stable throughout the construction process. Each segment was lifted into place using specialized cranes and temporarily supported until the adjacent segments were connected and the concrete joints cured. One of the significant challenges during construction was managing the tidal fluctuations and river traffic. To address this, engineers implemented a detailed construction schedule that accounted for tidal variations and coordinated with local authorities to minimize disruptions to river navigation. Temporary cofferdams were constructed around the piers to provide dry working conditions during low tide, allowing for precise placements of concrete and other materials. The bridge's design also included provisions for seismic activities and thermal expansion. Expansion joints were incorporated into the structure to accommodate temperature variations and prevent cracking. These joints, made of flexible materials, allowed the bridge to expand and contract with changes in temperature without compromising structural integrity.
The Al Maktoum International Airport, also known as Dubai World Central, is undergoing a massive expansion. Located in Jebel Ali, this ambitious project aims to make it the largest airport in the world by 2050. Approved in 2014, the $34.8 billion plan is managed by Dubai Aviation Engineering Projects. The expansion will increase passenger capacity to more than 268 million annually, 5 times that of Dubai International Airport. Phase 1 of the expansion began in 2016. This stage involves the construction of 2 4.5-kilometer long Code F runways, allowing simultaneous operations. Equipped with Cat 3IB instrument landing systems, the runways ensure smooth operations even in low visibility. A new 165,000 square meter terminal will handle 35 million passengers annually, while 2 massive satellite concourses will manage an additional 130 million passengers. Each concourse will feature 200 wide-body aircraft stands and advanced automated transport systems. These systems include 6 train tracks connecting terminals and concourses, ensuring seamless passenger movement. Phase 1 will also see the construction of a multi-level car park for 6,000 vehicles, enhancing accessibility. Phase 2 will add 2 more runways, bringing the total to 5, and a new terminal on the airport's east side. The concourses will form a mega structure covering 2.3 million square meters with 400 contact gates. Shopping, dining, and entertainment options will enrich the passenger experience in these state-of-the-art facilities. The expanded airport incorporates advanced technologies to improve passenger flow and reduce congestion. Biometrics and smart tracking will enable seamless movement through terminals. automated baggage systems, including bots for curbside drop-off, will simplify the travel process. These innovations ensure that DWC offers a world-class travel experience. The airport is designed to handle diverse aviation needs, from commercial to VIP and diplomatic flights. It will also accommodate crisis flights with specialized facilities, maintaining the reputation of DWC for versatility. By integrating cutting-edge technologies and sustainable practices, the airport sets a benchmark for future aviation projects. The construction employs mobile batching plants for on-site concrete production. Advanced cranes are used for assembling terminal megastructures, and automated laser-guided machines ensure precise runway leveling. Prefabricated steel components are transported by oversized vehicles, while drones monitor progress and enhance construction safety and precision. High-performance insulated buildings and solar glazing minimize energy consumption. The strategic location of DWC connects it seamlessly with the existing metro system, motorways, and seaports in Dubai. Once completed in 2030, the airport will integrate transport modes, logistics, and value-added services, including manufacturing and assembly, in a single free economic zone. The Governor Mario M. Cuomo Bridge, which replaced the aging Tappan Zee Bridge, is one of the most significant bridge projects in the history of New York. Costing $4 billion, this twin-span cable-stayed bridge stretches 3.1 miles across the Hudson River, connecting Rockland and Westchester counties. Completed in 2018, it represents a triumph of modern engineering and infrastructure innovation. The bridge features 2 spans, each supporting 8 lanes of traffic with a shared pedestrian and bike path, offering scenic views of the Hudson River. Its design includes sleek cable-stayed towers, which not only enhance its aesthetic appeal, but also provide structural efficiency. The lighting system incorporates energy-efficient LEDs that illuminate the bridge in vibrant colors for special occasions. Additionally, the bridge is equipped with state-of-the-art monitoring systems to ensure structural health and safety. Building the Cuomo Bridge required innovative methods to minimize environmental and community impact. Engineers employed precast concrete sections, which were manufactured off-site and transported to the construction area, reducing on-site work and improving efficiency. The foundation consists of large diameter steel piles driven deep into the riverbed to anchor the bridge securely. To accelerate the construction timeline, a custom-built floating crane, nicknamed iLift NY, was used to lift massive bridge components into place. The project emphasized sustainability, incorporating durable materials to extend the bridge's lifespan to 100 years. The bridge's design reduces maintenance needs, and its LED lighting system is energy efficient. Special care was taken to protect the Hudson River's ecosystem during construction, including the creation of artificial habitats for fish. The Cuomo Bridge has improved traffic flow for 35,000 daily vehicles, reducing congestion and enhancing safety. It has also revitalized the regional economy by creating thousands of construction jobs and stimulating local businesses. The pedestrian and bike path further enhances community access and promotes eco-friendly transportation. While the bridge is celebrated as an engineering feat, it faced criticism for its high cost and project delays. Despite these challenges, it stands as a vital link for the transportation network in New York.
The Oroville Dam in California, United States, is the tallest dam in the country at 770 feet, underwent significant reconstruction following the spillway failure in 2017. The reconstruction project, completed in 2019, involved extensive engineering and construction efforts to restore the dam's safety and functionality. The reconstruction focused on the main and emergency spillways, both of which were damaged during the 2017 incident. The project began with the demolition of the damaged sections, followed by the excavation and preparation of the foundation. This involved the removal of unstable materials and the installation of drainage systems to manage groundwater and prevent future erosion. The main spillway was reconstructed using high-strength roller-compacted concrete, a technique that involves placing and compacting layers of concrete using heavy rollers. This method provides a durable and erosion-resistant surface, capable of withstanding high water flows. The RCC was placed in layers, each approximately 12 inches thick, and compacted to achieve the required density and strength. The emergency spillway was reinforced with a new concrete weir and an extensive network of concrete walls and slabs, designed to control water flow and prevent erosion. The construction of these structures required precise formwork and concrete placement techniques, ensuring that the new spillway could handle extreme flood events. One of the significant challenges during the reconstruction was managing the continued operation of the dam and reservoir. This required careful coordination and planning, including the use of temporary spillways and water management systems to ensure the safety of downstream communities. The project also involved extensive monitoring and testing to verify the performance of the new structures and ensure compliance with regulatory standards. The Oroville Dam Reconstruction Project demonstrates the application of advanced engineering and construction techniques to address critical infrastructure needs. The project restores the dam's safety and functionality, ensuring the reliable management of California's water resources. The successful completion of this complex and challenging project showcases the capabilities of modern civil engineering to solve significant infrastructure challenges.
Let's move over to India next to talk about the Dholera Solar Power Plant, which stands as a monumental achievement in renewable energy. Spread over 11,000 hectares in the Dholera Special Investment Region, the plant has a planned capacity of 5 gigawatts. The project, with an estimated cost of $3.8 billion, will generate enough electricity to power approximately 5 million households, reducing dependency on fossil fuels. Situated approximately 80 kilometers from Ahmedabad, the Dholera Solar Power Plant leverages advanced technology to maximize efficiency. The plant will utilize advanced photovoltaic technology, including bifacial solar panels that capture sunlight from both sides, enhancing efficiency. Cutting-edge tracking systems will ensure maximum energy output by aligning panels with the movement of the sun. Adani Green Energy developed the first phase, a 700 megawatt facility spread across several kilometers. Fixed and tracking solar panels are carefully placed to optimize solar energy capture throughout the day. These panels channel power through central inverters, converting direct current into alternating current for integration into the grid. The geographical challenges of the site required innovative solutions. The low-lying intertidal region faces frequent flooding and corrosion risks. Engineers use geospatial technology to plan the layout and ensure optimal panel placement. The solar modules, built with polycrystalline silicon technology, are mounted on concrete foundations raised to 450 millimeters to protect them from tidal and flood effects. This design minimizes environmental impact while enhancing durability and energy production. Power generated at Dholera is transmitted through an intricate 49-kilometer underground cable network. High and low voltage lines transport electricity from the panels to pooling substations and onward to a 400 kilovolt Power Grid Corporation of India substation. This ensures reliable power delivery even in adverse conditions. The construction employs solar panel mounting machinery, automated stringing machines for wiring, and high-capacity cranes for installing massive photovoltaic arrays. Ground leveling is performed by graders, while robots are used for panel cleaning. Advanced trenching machines aid in laying underground power cables for grid integration. The Dholera project is seamlessly integrated with regional infrastructure, benefiting from its proximity to roads, railways, airports, and seaports. Canals from the Narmada River supply water for maintenance and cooling, distributed across the site via underground pipelines and pumping stations. This efficient water management system reduces wastage, and supports the long-term sustainability of the park. The project also includes modern telecommunication infrastructure, with radio masts and towers supporting antennas for integrated services. The solar modules, with over 15% photoelectric conversion efficiency, are protected with thermoplastic junction boxes and silicone rubber edge sealing, ensuring longevity and performance. It's time for a much taller project called 270 Park Avenue, which is soon to be the global headquarters of JP Morgan Chase. Towering 1,388 feet with 60 stories, this state-of-the-art structure redefines the workplace with cutting-edge technology, sustainability, and architectural innovation. The previous structure at 270 Park Avenue, built in the late 1950s, was designed for 3,500 employees. However, as JP Morgan Chase grew, so did its needs. The new tower, conceptualized as a timeless addition to the skyline in New York, will accommodate up to 14,000 employees. Its design celebrates iconic architecture in legacy while embracing the future of workplace environments with flexibility and collaboration at its core. The building has a state-of-the-art gym, gourmet dining, and outdoor terraces with skyline views. The project began with the demolition of the original building in 2019, marking one of the largest voluntary demolitions of a structure in history. Remarkably, 97% of the materials from the old building were recycled or upcycled, far exceeding industry standards for green building projects. The new tower is being built using a hybrid structural system of steel and reinforced concrete. This all-electric tower will be the largest in New York City with net zero operational emissions. Powered entirely by renewable energy from a New York State hydroelectric plant, the building incorporates advanced systems to ensure energy efficiency. Features include triple-pane glazing on the facade and automatic solar shades integrated with HVAC systems. These also include intelligent building technology that uses sensors and AI to optimize energy consumption. Water efficiency is another highlight, with advanced storage and reuse systems reducing water consumption by over 40%. The terraces in the building and a large public plaza offer natural green spaces, enhancing urban biodiversity and promoting well-being for workers and visitors alike. The unique structural system of the building employs fan columns and triangular bracing, enabling it to lift 80 feet off the ground. This creates an expansive open area at street level, offering 2.5 times more outdoor space along Park and Madison Avenues. Wider sidewalks and public plazas make the area more pedestrian-friendly while maintaining a seamless architectural flow.
The Waimea Community Dam in New Zealand is a significant project aimed at providing a reliable water supply for the Tasman region. The construction of this earth-filled dam involved complex engineering techniques to address the unique geological and environmental challenges of the site. The dam, standing 174 feet tall and 1,210 feet long, is designed to store approximately 13 billion gallons of water. The construction process began with extensive site preparation, including the excavation of a large foundation trench to ensure a stable base for the dam. This involved removing unsuitable materials and replacing them with engineered fill. The foundation was then treated with a combination of grouting and drainage systems to manage groundwater and prevent seepage. These measures are critical for maintaining the dam's structural integrity and ensuring long-term stability. The dam's core is constructed using impervious clay, which acts as a barrier to prevent water from seeping through the structure. This clay core is flanked by zones of carefully compacted earthfill, providing support and stability. The construction of these zones involved precise layering and compaction techniques to ensure that each layer met the required specifications for density and moisture content. This meticulous process helps to prevent settlements and maintain the dam's structural integrity over time. To enhance the dam's safety, a robust spillway system was designed to handle potential overflow during periods of heavy rainfall. The spillway consists of a concrete chute and energy dissipation structures, which are designed to safely convey excess water downstream without causing erosion or damage to the dam. The design and construction of the spillway required careful planning and execution, taking into account the potential impacts of extreme weather events and climate change. The construction of the Waimea Community Dam also included the development of extensive monitoring and control systems. These systems involve the installation of piezometers, inclinometers, and other instrumentation to monitor the dam's performance and detect any potential issues early. This real-time data is crucial for the ongoing management and maintenance of the dam, ensuring that it operates safely and effectively.
Let's travel over to Green Riyadh, a visionary project redefining urban landscapes in Saudi Arabia. Alongside King Salman Park, Sports Boulevard, and Riyadh Art, the 4 Riyadh projects are projected to cost around $23 billion. The project is part of Saudi Vision 2030, set to promote Riyadh as one of the most livable cities in the world. Green Riyadh aims to plant 7.5 million trees across the city, targeting 9.1% green coverage of the total area in the capital. Neighborhoods, schools, and streets will be adorned with native shade species, creating a harmonious urban forest. Over 3,300 neighborhood gardens and 43 parks will be established, complemented by tree-lined roads stretching 16,400 kilometers. The urban fabric in Riyadh will be refreshed, enhancing air quality and reducing temperatures by up to 15 degrees Celsius in intensively greened areas. Parks are integral to the vision of Green Riyadh. Al Aruba Park, spanning 754,000 square meters, will feature 3 kilometers of elevated walkways offering panoramic city views. Its unique design incorporates augmented reality experiences and water bodies integrated with Al Laysan Valley. 3 additional parks in Al Munsia, Al Rimal, and Al Qadisiyah will cover 550,000 square meters and include walking trails, cycling paths, and open spaces for festivals and sports. Together, these parks will host over 1.2 million trees and shrubs, promoting biodiversity and environmental awareness. The construction of Green Riyadh incorporates advanced techniques to establish sustainable infrastructure. Machinery includes automated tree planters, GPS-guided excavation equipment for park layouts, and water-efficient drip irrigation systems. Heavy-duty trucks transport large volumes of soil and plants, while drones are used for aerial mapping and monitoring of the project. A new water treatment network will provide 1 million cubic meters of recycled water daily for irrigation. Plant nurseries will supply seedlings, ensuring the project meets its ambitious planting targets. Enhanced urban regulations and public awareness campaigns will encourage community engagement, making this transformation a collaborative effort. The economic impact is equally profound. Green Riyadh is projected to yield $19 billion by 2030 through reduced healthcare costs, lower electricity bills, and increased real estate values. The private sector will also gain opportunities in nurseries, landscaping, and irrigation, fostering local industries. By 2030, Green Riyadh aims to position the city among the top 100 livable cities globally. Let's travel over to the Hudson Tunnel Project, a $16 billion undertaking that seeks to transform rail infrastructure between New York and New Jersey. This project is critical to modernizing the Northeast Corridor, the most heavily traveled rail line in the United States. Once completed, it will ensure seamless transit for Amtrak and New Jersey Transit passengers, improving reliability and safeguarding operations against future natural disasters. The existing North River Tunnel, built over a century ago, suffered severe damage during Superstorm Sandy in 2012. The storm left behind structural weaknesses, necessitating urgent rehabilitation. The NRT serves as the single passenger rail link between Manhattan and the western US connecting Washington, D.C. to Boston. Without upgrades, the tunnel bottleneck risks a daily $100 million economic impact, reflecting the 20% contribution of the Northeast Corridor to the national economy. The project involves building a 2.4-mile double-track tunnel beneath the Hudson River, stretching from Bergen Palisades in New Jersey to Manhattan. Central to its scope is the rehabilitation of the North River Tunnel, addressing extensive structural and flood damage sustained over the years. Then, a concrete casing at Hudson Yards will ensure a seamless connection to Penn Station, integrating the new infrastructure into the existing rail network. To safeguard rail operations from future extreme weather events, new floodgates will be installed, providing enhanced protection against rising waters. The tunnel will incorporate state-of-the-art engineering with advanced flood resilience measures. This includes a robust drainage system, climate-resistant materials, and modern ventilation for improved air quality. The construction utilizes state-of-the-art engineering technologies to address the unique challenges of tunneling beneath a riverbed. Tunnel boring machines excavate the 2.4-mile route, ensuring precise tunneling through dense geological formations. These massive machines carve through rock and soil while simultaneously installing precast concrete tunnel linings, providing immediate structural support. Advanced geotechnical monitoring systems track ground stability in real time, minimizing risks during construction. Meanwhile, robotic systems streamline the application of waterproofing membranes, ensuring the tunnel remains impervious to leaks. Scheduled for phased completion, the new tunnel is expected to open in 2035, with the rehabilitated NRT operational by 2038. Once completed, the Hudson Tunnel project will transform rail travel, accommodating nearly 200,000 passengers daily. The project is expected to create 72,000 new jobs and $19 billion in economic activity. But this is just one of the smaller mega projects on our list.
The Great Plains Power Station in Canada, located in Moose Jaw, Saskatchewan, is a natural gas-fired power plant designed to provide reliable and efficient energy supplies. Scheduled for completion in 2024, the project involves the construction of a 350-megawatt combined cycle power plant, utilizing advanced gas turbine technology. The construction process began with site preparation and grading, creating a stable foundation for the power plant infrastructure. This involved extensive earthworks, including excavation and compaction, to ensure that the site could support the heavy equipment and structures. The foundations for the gas turbines and other critical components were constructed using reinforced concrete, designed to withstand dynamic loads and provide long-term stability. One of the primary engineering challenges was the installation of the gas turbines and heat recovery steam generators. The gas turbines, manufactured by Siemens, are among the most efficient in the world, capable of converting natural gas into electricity with high efficiency and low emissions. The installation of these turbines required precision alignment and balancing, ensuring optimal performance and reliability. The HRSGs, which capture waste heat from the gas turbines to generate additional electricity, were assembled on-site using prefabricated components, minimizing the construction time and ensuring high-quality fabrication. The power plant's design incorporates advanced cooling systems, including air-cooled condensers, which reduce water consumption and environmental impact. These condensers, constructed using modular components, were installed using large cranes and specialized lifting equipment. The use of air-cooled technology is particularly important in regions with limited water resources, ensuring that the power plant operates sustainably.
Let's talk about the Brooklyn-Queens Expressway, officially known as Interstate 278. Constructed between 1939 and 1964, this iconic roadway is not just a vital piece of infrastructure, but also a symbol of urban planning challenges. Designed by Robert Moses, the BQE spans 11.7 miles, serving as a critical link for commuters, freight traffic, and tourists navigating the city. The BQE was initially conceived as part of an ambitious plan presented by Moses to modernize New York's roadways. Built to accommodate mid-20th century traffic demands, it became a significant economic driver for the region. However, the design of the expressway, including its cantilevered triple-deck section along the Brooklyn Heights Promenade, was a marvel of its time. It lacked foresight for the growing population and vehicle load of the 21st century. Decades of wear and tear have taken a toll on the BQE, particularly its aging infrastructure, including corroding steel beams and crumbling concrete. The triple cantilever section of the expressway, carrying up to 150,000 vehicles daily, is now considered structurally unsound, leading to urgent calls for reconstruction. The BQE features multiple sections, including elevated, sunken, and cantilevered structures. The cantilevered portion, perched beneath the Brooklyn Heights Promenade, is a unique engineering feat, but presents significant challenges for rehabilitation. It supports 3 layers of traffic and a pedestrian promenade, requiring innovative solutions for repair without disrupting the bustling traffic flow or the community above. Current discussions for the BQE's overhaul include replacing the deteriorating sections with modern materials and designs to accommodate contemporary traffic demands. Estimated costs for reconstruction range from $1.7 billion to $4 billion, depending on the chosen plan. Proposals for the modernization of BQE include building a temporary roadway while repairing the cantilever. They'll probably reroute traffic through adjacent streets, or even convert sections into a boulevard to reduce vehicular congestion. Incorporating sustainable materials, advanced traffic management systems, and noise-reducing technology are integral to these plans. The deteriorating condition of BQE underscores the pressing need for investment in infrastructure.
The New Kalani Bridge in Sri Lanka, completed in 2020, is a significant infrastructure project aimed at improving connectivity between Colombo and its suburbs. This 6-lane bridge spans the Kalani River and incorporates several innovative construction techniques to address the challenges posed by the river's width and tidal variations. The construction process began with the installation of deep foundation piles, driven into the riverbed to provide a stable base for the bridge piers. These piles were made of high-strength steel and concrete, capable of withstanding the dynamic loads from both the bridge structure and river currents. The foundation work required precise geotechnical surveys and advanced piling techniques to ensure the stability and longevity of the structure. The bridge's main span, constructed using a steel box girder design, involved the prefabrication of large segments off-site. These segments were transported to the construction site using barges and lifted into place using heavy lift cranes. The use of prefabrication allowed for high-quality control and reduced on-site construction time. Each girder segment was meticulously aligned and welded to form a continuous structure, ensuring the bridge's strength and durability. One of the unique features of the New Kalani Bridge is its cable-stayed design, with cables arranged in a fan configuration. These cables, made of high-strength steel, support the main span and provide additional stability. The cable-stayed design allows for a longer span and reduces the number of piers needed in the river, minimizing environmental impact and improving navigation clearance for river traffic. The construction also included the development of approach ramps and road connections, integrating the bridge into Colombo's existing transportation network. This required extensive earthworks and the construction of retaining walls and embankments to support the elevated roadways. The approach ramps were designed to provide smooth transitions and minimize disruptions to traffic flow. The Leonard P. Zakim Bunker Hill Memorial Bridge in Boston, completed in 2003, is a notable example of modern engineering and construction. The cable-stayed bridge, part of the Big Dig project, required innovative techniques and precise execution. The bridge features 2 inverted Y-shaped towers, each 295 feet tall, constructed using reinforced concrete. The climbing formwork system used for these towers allowed continuous concrete pouring, ensuring structural integrity and minimizing construction time. The main span of the bridge, stretching 745 feet, is supported by 116 high-strength steel cables, arrived in a harp configuration. These cables were meticulously tensioned to ensure even load distribution. Each cable was anchored at the bridge deck and tower, requiring precise calculations to maintain balance and stability. The deck itself was constructed using precast concrete segments, which were transported to the site and assembled using a launch gantry, minimizing disruptions and expediting the construction process. Maintaining traffic flow on the existing I-93 highway while building the new bridge was a significant challenge. This required a series of temporary supports and careful staging of construction activities. Additionally, the bridge had to be integrated within the city's underground Central Artery Tunnel, necessitating complex coordination between different construction teams. Extensive geotechnical engineering ensured the stability of the bridge foundations, which were anchored in deep bedrock to withstand the weight and dynamic loads of the structure. The Zakim Bridge's design incorporated seismic considerations. Given Boston's susceptibility to earthquakes, engineers used advanced modeling to simulate seismic events and ensure the bridge's resilience. The towers and deck were designed to move independently, allowing them to absorb and dissipate energy during an earthquake, minimizing structural damage. One of the issues faced during construction was soil stability and water infiltration, which required additional measures such as dewatering and ground improvement techniques. However, these challenges were overcome through innovative engineering solutions and meticulous planning. The bridge's design also includes provisions for thermal expansion and contraction, with expansion joints made of flexible materials to allow the bridge to expand and contract with changes in temperature without compromising structural integrity.
Next up, we have to talk about U-Tapao Aviation City, which is a $9 billion mega project that aims to transform U-Tapao International Airport into a world-class aviation and logistics hub. This airport is near popular tourist destinations like Pattaya, Koh Samet, and the Rayong fruit orchards. Located in Rayong province in Thailand, this project spans 2,570 acres, aiming to transform U-Tapao International Airport into the third major gateway in Bangkok. This location offers strategic advantages. U-Tapao Aviation City is connected to Suvarnabhumi and Don Mueang airports by a high-speed rail network. This ensures seamless travel across Thailand and easy access to ASEAN cities. Major industrial zones and ports, including Liam Chabang and Map Ta Phut, are nearby, enhancing its logistics potential. U-Tapao International Airport will serve as a hub for air cargo and passenger travel. Designed to handle increased traffic, it will significantly boost the logistics performance in Thailand. The airport will connect with double-track railways, expressways, and industrial ports, ensuring efficient transportation for goods and people. The project will add a new terminal designed to handle 60 million passengers annually, significantly enhancing capacity. U-Tapao Aviation City will also host an aerospace center dedicated to aircraft maintenance, repair, and overhaul, a vital service for regional and international airlines. Furthermore, an aviation training center will be established to develop a skilled workforce, ensuring the sustainability of the expanding aviation industry in Thailand. The project also features the Eastern Airport City, a smart, sustainable urban center. It will offer creative living spaces, innovative work environments, and round-the-clock entertainment. This area is designed to attract businesses, tourists, and investors, making it a thriving economic hub. The development aligns with Thailand's push for economic growth. The EEC Act offers special investment incentives, including tax exemptions and long-term land leases. These benefits aim to attract global investors to U-Tapao and its surrounding regions. Construction is underway, with a focus on sustainability and innovation. The project employs TBMs for underground facilities, advanced concrete pouring machinery for airport runways, and gantry cranes for assembling large hangars. Precision-guided pile drivers lay robust foundations, and automated systems streamline construction of the curved roof structures in the terminal. Environmental monitoring devices ensure sustainable building practices. Currently, the airport terminal, logistics facilities, and smart city elements are being developed to world-class standards. Completion is projected for 2028, marking a new era for economic and logistical ventures in Thailand.
The Tappan Zee Bridge in New York, officially known as the Governor Mario M. Cuomo Bridge, was completed in 2018. This replacement for the original Tappan Zee Bridge required innovative engineering and construction techniques to span the Hudson River and address the demands of modern traffic. The construction began with the installation of deep foundation piles driven into the riverbed to provide a stable base for the bridge piers. These piles, made of high-strength steel and concrete, were driven to depths of over 300 feet to reach bedrock, ensuring stability and durability. The foundation work required precise geotechnical surveys and advanced piling techniques to ensure stability and longevity of the structure. The bridge's main span, constructed using a cable-stayed design, features two 419-foot towers and support the bridge deck with 192 cables. The cable-stayed design allows for longer spans and fewer piers in the river, reducing environmental impact and improving navigational clearance for river traffic. The construction of the towers involved the use of jump forms, which allowed for continuous concrete pouring and ensured structural integrity. The bridge deck was constructed using precast concrete segments, which were transported to the site and lifted into place using specialized cranes. Each segment was precisely aligned and connected to form a continuous deck. The use of precast segments allowed for high-quality control and reduced on-site construction time. The segments were pre-tensioned with high-strength steel cables to enhance the bridge's load-bearing capacity and ensure long-term stability. One of the significant challenges during construction was managing the river's tidal fluctuations and weather conditions. To address this, engineers implemented a detailed construction schedule that accounted for tidal variations and coordinated with local authorities to minimize disruptions to river navigation. Temporary cofferdams were constructed around the piers to provide dry working conditions during low tide, allowing for the precise placement of concrete and other materials. The Tappan Zee Bridge also features advanced safety and monitoring systems. The bridge is equipped with sensors that monitor structural health in real time, providing data on load distribution, temperature, and vibrations. This information is used to ensure the bridge's safety and performance, allowing for timely maintenance and repairs. The construction of the Tappan Zee Bridge demonstrates the application of advanced engineering and construction techniques to create a modern, efficient, and resilient infrastructure asset. The bridge significantly improves traffic flow and connectivity in the Hudson Valley region, addressing the challenges of accommodating both road and river traffic in a densely developed area. The Hisingsbron Bridge in Gothenburg, Sweden, a vertical lift bridge, is a remarkable engineering project aimed at replacing the aging Godalv Bridge. Scheduled for completion in 2021, the Hisingsbron Bridge stands out for its innovative design and construction techniques. The bridge spans approximately 1,300 feet and features a vertical lift mechanism, allowing it to accommodate both road and maritime traffic efficiently. The construction began with the installation of deep foundation piles, driven into the riverbed to provide a stable base for the bridge piers. These piles were made of high-strength steel and concrete, capable of withstanding the dynamic loads from both the bridge structure and passing ships. This foundation work required precise geotechnical surveys and advanced piling techniques to ensure the stability and longevity of the structure. The bridge's main span is constructed using steel box girders, which are prefabricated off-site and transported to the construction site. These girders were then lifted into place using heavy lift cranes and connected to the piers. The use of prefabrication allowed for high-quality control and reduced on-site construction time. Each girder segment was meticulously aligned and welded to form a continuous structure, ensuring the bridge's strength and durability. One of the unique features of the Hisingsbron Bridge is its vertical lift mechanism, which allows the central span to be raised to a height of 150 feet, providing clearance for maritime traffic. The lifting system consists of counterweights and powerful electric motors, designed to operate smoothly and reliably. The bridge's control system includes advanced sensor and automation technology, allowing for precise and efficient operation. The construction also included the development of approach ramps and road connections, integrating the bridge into Gothenburg's existing transportation network. This required extensive earthworks and the construction of retaining walls and embankments to support the elevated roadways. The approach ramps were designed to provide smooth transitions and minimize disruptions to traffic flow.
The Westgate Tunnel project in Melbourne is a significant infrastructure initiative designed to alleviate traffic congestion and improve travel times in one of Australia's busiest urban areas. The $6.7 billion project involves constructing a 4-mile toll road with twin tunnels under Yarraville, a new bridge over the Maribyrnong River, and the widening of the Westgate Freeway. The project is a key component of the broader Victorian government's infrastructure plan to modernize and enhance the city's transport network. The tunnels will be constructed using massive tunnel boring machines, each weighing 4,000 tons and stretching 300 feet long. These tunnel boring machines are designed to excavate through diverse geological conditions, including soft clays and basalt rock, while simultaneously installing precast concrete segments to form the tunnel walls. Managing the disposal of the enormous volumes of excavated material is a key challenge, and this will be transported to designated sites for reuse or environmentally safe disposal. Advanced ventilation and air quality monitoring systems will ensure the safety of workers and the surrounding community. Noise and vibration mitigation measures are crucial to minimize the impact on nearby residents. The new cable-stayed bridge over the Maribyrnong River is designed to accommodate increased traffic volumes and enhance structural resilience against seismic activities. The project's integration of smart traffic management systems aims to optimize traffic flow and reduce congestion. Upon completion, the Westgate Tunnel is expected to significantly cut travel times, reduce congestion on the Westgate Bridge, and provide a much-needed alternative route for Melbourne's commuters and freight transport. The project also promises to enhance Melbourne's transport network by creating new cycling and pedestrian pathways, connecting key parts of the city and contributing to a more sustainable urban environment. Additionally, the construction phase is expected to generate thousands of jobs, providing a significant boost to the local economy. The Xinjiang Solar Power Plant in China is one of the world's largest solar farms, covering over 30 square miles in the Gobi Desert. This massive renewable energy project is set to generate 2 gigawatts of electricity, enough to power around 1.5 million homes annually. The construction of the plant involves the installation of millions of photovoltaic panels, mounted on advanced tracking systems that follow the sun's path to maximize energy capture. Engineers have designed these systems to withstand the harsh desert environment, including extreme temperatures and high winds. One of the key challenges in this project is the logistics of transporting and installing such a vast number of solar panels and supporting structures in a remote location. To address this, the project employs a modular construction approach, allowing for efficient assembly and scalability. Additionally, innovative dust mitigation techniques are implemented to maintain panel efficiency, such as using anti-dust coatings and robotic cleaning systems. The plant is connected to the grid via high-voltage direct current transmission lines, which are capable of transmitting electricity over long distances with minimal losses. The project also incorporates energy storage solutions to ensure a stable supply of electricity, even during periods of low solar irradiance. These energy storage systems are crucial for balancing supply and demand, enhancing grid stability. This solar power plant represents a significant step towards reducing carbon emissions and promoting sustainable energy development in China. By harnessing the vast solar potential of the Gobi Desert, the project not only contributes to China's renewable energy targets, but also sets a benchmark for large-scale solar energy projects worldwide. The plant's success could pave the way for similar projects in other desert regions across the globe, demonstrating the viability of solar power as a major energy source. The project will also stimulate economic development in the region by creating jobs and providing a reliable energy source for local industries. The Rome Metro Line C extension is an ambitious project aimed at expanding Rome's metro system to improve connectivity and reduce traffic congestion in the city. The extension adds several new stations and 11 miles of track to the existing line, stretching from central Rome to the suburbs. The project involves complex tunneling operations beneath the historic center of Rome, requiring careful excavation to avoid damaging ancient structures and archaeological sites. Tunnel boring machines equipped with state-of-the-art ground-penetrating radar are used to detect and navigate around sensitive areas. The construction also incorporates advanced engineering techniques, such as the use of pre-cast tunnel segments to accelerate the build process and enhance structural integrity. One of the significant challenges is managing the excavation and removal of spoil in a densely populated urban area. This is addressed through a combination of conveyor systems and specialized transport vehicles to minimize disruption to daily city life. The new stations are designed with modern architectural elements, integrating seamlessly with Rome's historic aesthetics, while providing improved accessibility features like elevators and escalators. The project also includes upgrading the existing stations and infrastructure to accommodate the increased passenger capacity. Advanced safety systems, including fire detection and suppression, as well as real-time passenger information systems, are installed to enhance commuter experience. The extension also incorporates green building standards, ensuring energy-efficient station operations and reduced carbon footprints. Upon completion, the Metro Line C extension will significantly reduce travel times, improve urban mobility, and contribute to the reduction of air pollution by encouraging the use of public transportation. The project is expected to transform the commuting experience in Rome, making it more efficient and reliable, and enhancing the overall quality of life for residents and visitors alike. The extension will also support the city's economic development by improving access to key commercial and cultural districts. The Intuit Dome is a state-of-the-art sports and entertainment arena currently under construction in Los Angeles, set to be the new home for the Los Angeles Clippers NBA team. This $1.8 billion project features a futuristic design with a seating capacity of 18,000, providing fans with an unparalleled viewing experience. The construction incorporates advanced engineering techniques, such as a cantilevered steel roof structure that eliminates the need for interior columns, ensuring unobstructed views from every seat. The arena is equipped with cutting-edge technology, including a high-definition scoreboard that wraps around the entire arena, and an advanced sound system for an immersive audio experience. One of the major challenges is the integration of sustainable building practices. The Intuit Dome aims to be a net-zero energy building, utilizing a combination of solar panels, energy-efficient systems, and innovative water conservation methods. The project also includes the construction of a multi-story parking structure and extensive landscaping with native plants to create a welcoming environment for fans. Advanced construction methods, such as prefabrication and modular assembly, are used to streamline the building process and reduce construction time. The arena will also feature numerous amenities, including luxury suites, a training facility, and spaces for community events. Once completed, the Intuit Dome will not only serve as a premier sports venue, but also as a catalyst for economic development in the surrounding area, creating jobs and attracting visitors to Los Angeles. The project underscores the importance of integrating modern design with sustainability, setting a new standard for future sports facilities worldwide. The Intuit Dome is poised to become a landmark in Los Angeles, drawing millions of visitors annually and significantly boosting the local economy through tourism and event hosting. The project also includes significant community engagement initiatives, ensuring that the benefits of the new arena extend to the local population through improved infrastructure and social programs. The construction utilizes advanced machinery, including mobile cranes, steel erection rigs, and prefabrication technology, to ensure precise and efficient assembly of the structure. The Zojila and Z-Morh tunnel projects in India are monumental infrastructure developments aimed at improving year-round connectivity between the Kashmir Valley and Ladakh. The Zojila Tunnel, stretching over 9 miles, is set to be one of the longest and highest altitude road tunnels in the world, providing all-weather access through the Himalayan range. The Z-Morh Tunnel at 4.2 miles serves as a crucial link to the Zojila Tunnel. These projects involve cutting through some of the most challenging terrains, characterized by extreme weather conditions and high seismic activity. Advanced tunnel boring machines and new Austrian tunneling methods are employed to navigate these challenges, ensuring precision and safety. One of the primary challenges is the stabilization of loose rock and soil, which is addressed through ground freezing techniques and the installation of rock bolts and shotcrete. The tunnels are designed with multiple safety features, including emergency exits, ventilation systems, and fire detection and suppression systems. During construction, extensive environmental monitoring is conducted to mitigate impacts on the fragile mountain ecosystem. The projects also involve the construction of access roads, bridges, and support infrastructure to facilitate transportation and logistics. These access routes are critical for transporting materials and workers to the remote construction sites, ensuring timely progress. Once completed, these tunnels will drastically reduce travel time, enhance trade and tourism, and improve the strategic mobility of the Indian Armed Forces in this remote region. The projects will also provide significant socio-economic benefits to the local communities, improving access to essential services and boosting economic activities. Enhanced connectivity will foster regional development and integration, making it easier for people and goods to move between these historically isolated areas. Additionally, the tunnels will improve safety and reliability for travelers, reducing the risk of accidents and road closures due to adverse weather conditions. The construction of these tunnels employs specialized machinery such as rock drilling rigs, ground freezing units, and advanced tunnel lining equipment to ensure structural stability and safety. The new Everton Stadium, also known as Bramley-Moore Dock Stadium, is a landmark development for Everton Football Club in Liverpool, United Kingdom. This 50-20-seat stadium is being constructed on the historic Bramley-Moore Dock, a UNESCO World Heritage Site, blending modern architecture with the area's rich industrial heritage. The project involves extensive groundworks to stabilize the dock, including the use of advanced piling techniques and ground improvement methods to ensure a solid foundation. One of the major engineering challenges is preserving the historic dock wall while integrating it into the stadium's design. The construction also includes a complex drainage system to manage water levels and prevent flooding. The stadium features a striking brick facade, echoing Liverpool's historic buildings, and a steep, single-tier home stand to enhance the matchday atmosphere. Inside, the stadium is equipped with state-of-the-art facilities, including hospitality suites, retail spaces, and a museum celebrating the club's history. Advanced construction techniques, such as the use of prefabricated components and modular construction, are employed to ensure efficiency and precision. Sustainability is a key focus, with the project incorporating renewable energy sources, energy-efficient systems, and sustainable materials. The construction also emphasizes the use of local materials and labor, supporting the regional economy. Once completed, the new Everton Stadium will not only provide a world-class venue for football, but also serve as a catalyst for the regeneration of the surrounding area, creating jobs and boosting the local economy. The stadium is set to become an iconic landmark in Liverpool, attracting tourists and sports enthusiasts from around the world. The project also includes community engagement initiatives, ensuring that the new stadium benefits the local population through improved infrastructure and social programs. Additionally, the stadium's design incorporates advanced acoustics and lighting systems, enhancing the overall spectator experience and making it a premier venue for various events beyond football. The construction process utilizes heavy machinery such as pile drivers, concrete mixers, and prefabrication assembly lines to ensure timely and accurate completion of the project. The Chenab Bridge in India is an engineering marvel, set to be the world's highest railway bridge upon completion. Spanning the Chenab River in the Himalayas, this bridge is part of the Udhampur-Srinagar-Baramulla Rail Link project, aiming to improve connectivity in the region. The bridge's arch design, stretching 1,315 feet across and rising 1,178 feet above the river, is a testament to advanced engineering and construction techniques. The construction involves the use of high-strength steel to withstand the challenging weather conditions and seismic activity in the region. One of the primary challenges is the erection of the massive arch, which is being done using a combination of cantilever and cable crane methods. Extensive wind tunnel testing and seismic analysis have been conducted to ensure the bridge's stability and safety. The project also includes the construction of approach roads, tunnels, and viaducts to connect the bridge to the existing rail network. Advanced construction methods, such as incremental launching and balanced cantilever construction, are employed to ensure precision and efficiency. The bridge is designed with multiple safety features, including automated monitoring systems to detect structural stresses and movements. Once completed, the Chenab Bridge will significantly reduce travel time, enhance trade and tourism, and provide a crucial link for the Indian railways in this remote and strategic region. The project also promises to boost the local economy by improving accessibility and creating jobs during the construction phase. The bridge will stand as a symbol of modern engineering prowess, attracting tourists and becoming a landmark in the region. Additionally, the improved rail connectivity is expected to facilitate the movement of goods and people, contributing to the economic development of the surrounding areas. The construction process itself has become a training ground for engineers, offering valuable experience in handling complex projects under challenging conditions. The construction of the Chenab Bridge employs specialized machinery such as cable cranes, hydraulic jacks, and high-precision surveying equipment to ensure accurate assembly and alignment of the bridge components. The Hefei-Wuhan high-speed railway in China is a major infrastructure project aimed at enhancing connectivity between the cities of Hefei and Wuhan. This 300-mile high-speed rail line is designed to support train speeds of up to 220 miles per hour, reducing travel time between the two cities to just over 1 hour. The project involves the construction of multiple tunnels, bridges, and viaducts to navigate the complex terrain. One of the key engineering challenges is the construction of the long tunnels through mountainous regions, which requires advanced tunnel boring machines and precise engineering techniques. The railway line is equipped with state-of-the-art signaling and communication systems to ensure safety and efficiency. To minimize environmental impact, extensive environmental assessments and mitigation measures are implemented, including wildlife crossings and noise barriers. The project also includes the construction of modern stations equipped with advanced passenger amenities and accessibility features. The Hefei-Wuhan high-speed railway is part of China's broader efforts to expand its high-speed rail network, promoting economic development and regional integration. Once completed, the railway line will provide a fast, efficient, and environmentally friendly transportation option, boosting connectivity and economic growth in the region. The project is expected to significantly reduce carbon emissions by providing a greener alternative to air and road travel. The Hefei-Wuhan high-speed railway will not only improve travel efficiency, but also stimulate economic activities in the regions it connects, fostering greater regional cooperation and development. The railway is also expected to enhance tourism by making it easier for travelers to access the cultural and historical attractions in both cities, further contributing to the local economies. The construction of the railway employs high-speed rail technology, including the use of continuous welded rail, slab track systems, and automated track-laying machines to ensure smooth and reliable train operations. The Doha Solar Park in India is one of the world's largest solar energy projects, designed to generate 5 gigawatts of electricity. Located in the Doha Special Investment Region in Gujarat, this solar park covers over 27,000 acres. The project involves the installation of millions of photovoltaic panels, advanced inverters, and extensive transmission infrastructure to connect the generated power to the grid. One of the major challenges is the harsh environmental conditions, including high temperatures and dust, which necessitate the use of durable and efficient solar technologies. To address this, the project employs bifacial solar panels, which can capture sunlight on both sides, and robotic cleaning systems to maintain panel efficiency. The solar park also includes energy storage solutions, such as large-scale battery systems, to ensure a stable supply of electricity. The construction involves a modular approach, allowing for phased development and scalability. Extensive environmental assessments are conducted to minimize impacts on the local ecosystem, including measures to protect wildlife and manage water resources sustainably. The project is designed to integrate seamlessly with the existing grid infrastructure, ensuring reliable power delivery. Once completed, the Doha Solar Park will significantly contribute to India's renewable energy capacity, reducing carbon emissions and promoting sustainable development. The project will also provide a boost to the local economy by creating jobs and fostering the growth of a clean energy industry in the region. By harnessing solar energy, the Doha Solar Park sets a precedent for future renewable energy projects, showcasing India's commitment to sustainable development. The project is expected to attract further investments in renewable energy, positioning India as a global leader in the clean energy sector. The solar park will also serve as a model for large-scale solar energy projects worldwide, demonstrating the potential of renewable energy to meet the growing energy demands sustainably. The construction process utilizes advanced machinery such as solar panel mounting systems, high-capacity cranes, and automated assembly lines to ensure efficient and precise installation of the solar arrays.